What if everything you see, everything you experience is only a fleeting fragment, a mere sliver of something infinitely more intricate, something beyond our comprehension? Imagine that the universe, as vast and complex as it is, might be nothing more than a projection, a hologram of a reality governed by dimensions we cannot even begin to perceive. What if, beneath the surface of our observable world, there exists a profound structure, so elaborate and hidden that it transcends our current understanding of physics and space? This possibility has intrigued theoretical physicists for decades. They've long speculated that the three-dimensional world we experience could merely be a small window into a far larger, more complex cosmos. The idea of hidden dimensions is not a wild notion pulled from the pages of science fiction novels. It's a serious hypothesis, one that might explain some of the most baffling and profound mysteries of the universe that we've yet to grasp. String theory, one of the most well-known and studied theories in modern physics, suggests that our universe exists in a multiverse with up to 11 dimensions. These dimensions are not all visible to us. In fact, many of them are so tightly curled, so compact, that we are completely unaware of their existence. Imagine for a moment that our reality is like a vast web, and most of its threads, these hidden dimensions, are invisible to the naked eye. These unseen dimensions could be influencing the very forces that shape our universe, controlling the fundamental aspects of reality, from gravity to the curvature of space-time itself. In physics, a dimension is defined as a fundamental aspect of space or time, a measurement that allows us to describe and make sense of the universe around us. The most familiar of dimensions are the three spatial ones: length, width, and height, which allow us to pinpoint the location of any object within our everyday world. These three dimensions provide us with the means to navigate our surroundings, to understand how we can move forward, backward, left, right, and up and down. Time, often referred to as the fourth dimension, is equally vital. It is through time that we understand when events occur, how they unfold, and how they relate to one another. Together, these four dimensions form the concept of space-time, a unified continuum that combines both space and time into a single, inseparable entity. This understanding helps explain much of the universe's structure, from the movement of planets to the behavior of light across vast distances. Yet, this framework of four dimensions is just the beginning. The theories that explore the fundamental nature of reality propose that there are far more dimensions than the ones we can directly experience. Some theories suggest that there could be extra dimensions that are so tiny, so tightly compacted, that we cannot perceive them using our current scientific tools or technology. These extra dimensions could potentially hold the key to understanding aspects of the universe that remain mysterious, such as the behavior of subatomic particles or the force of gravity. While we tend to think of dimensions as being tied to the familiar three spatial dimensions and the one dimension of time, the full picture of dimensions is far more complex. According to string theory, for example, there are 10 or even 11 dimensions. These extra dimensions exist at scales so small that they are curled up and imperceptible to our senses. Yet they are deeply intertwined with the fabric of the universe, affecting everything from the behavior of fundamental particles to the large-scale structure of the cosmos itself. These hidden dimensions could help us unlock answers to some of the biggest questions in modern physics. They may offer insight into the unification of all fundamental forces: gravity, electromagnetism, the weak force, and the strong force, something that has eluded physicists for over a century. The discovery of these extra dimensions could also help explain the mysterious nature of dark matter and dark energy, two of the most enigmatic phenomena in the universe, which constitute the majority of the universe's mass and energy, yet remain completely invisible to us. In everyday life, we are primarily aware of the four dimensions of space-time: three spatial dimensions, which describe the physical world we live in, and one temporal dimension, which describes the flow of events over time. These dimensions allow us to measure and describe the position of objects, the sequence of events, and the passage of time. They form the framework within which we understand the world around us and predict the behavior of objects. However, as we delve deeper into the nature of reality, we begin to realize that these four dimensions may only be a small part of the larger picture. In theoretical physics, the idea of higher dimensions is critical for explaining phenomena that can't be accounted for in our conventional understanding of space-time. For example, higher dimensions could provide a deeper understanding of the forces at play in the quantum realm, the microscopic world that operates under different rules from the macroscopic world we experience daily. These additional dimensions, though mathematically difficult to imagine, help explain some of the most fundamental aspects of the universe. In string theory, the very fabric of reality is thought to be made up of tiny vibrating strings, and the way these strings vibrate could depend on the additional dimensions that are present. The extra dimensions proposed in string theory are not simply extensions of the known dimensions. They represent entirely new directions of movement or measurement that are perpendicular to everything we know. For instance, consider the concept of a four-dimensional cube known as a tesseract. A tesseract exists in a dimension perpendicular to the three spatial dimensions we are familiar with. While it's nearly impossible to visualize such a shape in our three-dimensional world, its mathematical properties are essential for understanding higher dimensional spaces. These extra dimensions are more than abstract concepts. They offer a framework for understanding parallel universes, the nature of subatomic particles, and even the forces that govern the universe. Over the centuries, our understanding of dimensions has evolved. Ancient civilizations typically viewed the world through the lens of three spatial dimensions: length, width, and height. This view served practical purposes, from navigation to architecture, by providing a simple way to understand and interact with the world. With the advent of the scientific revolution in the 16th and 17th centuries, however, the concept of dimensions became more rigorous, leading to the development of mathematical tools such as the Cartesian coordinate system, which allowed us to describe points in space using numbers. In the 20th century, Albert Einstein's groundbreaking theory of relativity forever changed our understanding of dimensions. Einstein proposed that time, long considered a separate and independent entity, should be treated as a fourth dimension, inseparably linked to the three spatial dimensions of length, width, and height. This unification of space and time into space-time was a revelation, leading to profound implications for our understanding of gravity, the speed of light, and the structure of the universe. Today, theoretical physicists continue to explore the possibility of additional dimensions. String theory and other advanced theories propose that our universe could contain as many as 10 or 11 dimensions, most of which are hidden from view, curled up at scales far smaller than we can measure. These dimensions could hold the answers to some of the most perplexing questions in modern physics, such as the true nature of gravity, the origin of dark matter, and the unification of the fundamental forces. As we push the boundaries of our knowledge, the study of dimensions remains at the forefront of our quest to understand the universe. By exploring the possibility of higher dimensions, scientists are not just seeking answers to the deepest mysteries of the cosmos, they are working to rewrite the very laws of nature. What we once thought of as simple, familiar dimensions may turn out to be only a small part of a much grander and more complex reality. And in this exploration, we may be on one of the most significant breakthroughs in the history of science. These theories suggest that our universe may be only one in an unimaginably vast multiverse, existing alongside an infinite number of other universes, each potentially following its own set of physical laws. While these ideas remain speculative and theoretical, they continue to shape the direction of cutting-edge scientific research, deepening our exploration of the fundamental nature of reality. As our understanding of the cosmos advances, so too does the curiosity about dimensions beyond those we experience on a daily basis. When we talk about higher dimensions, we are stepping far beyond the world of familiar observable reality, venturing into a space where our senses cannot follow. Our everyday experience is governed by three spatial dimensions: length, width, and height. Time is considered a fourth dimension, an ever-flowing river that connects past, present, and future. Yet, theoretical physics proposes that this four-dimensional model may only scratch the surface of a more complex, multidimensional structure. Beyond these known dimensions, there could be other hidden dimensions that we are not equipped to perceive. These extra dimensions exist not in the realm of physical sensation, but in the abstract domain of mathematics, where they help explain complex phenomena that are not fully understood in the existing framework of physics. One of the most intriguing frameworks exploring these higher dimensions is string theory, which proposes that the most fundamental components of the universe are not point-like particles, as traditionally thought, but tiny, vibrating strings of energy. The vibrations of these strings, so minuscule that they are far smaller than even the subatomic particles we are familiar with, give rise to all known particles and forces. This theory not only suggests the existence of these tiny strings, but it also implies that the universe may be made up of up to 10 or even 11 dimensions, far surpassing the 4 dimensions we can directly experience. These additional dimensions, according to string theory, are not spread out in an easily observable manner. Instead, they are compactified or curled up in ways so tight that they cannot be detected by any of our instruments or senses. This compactification suggests that these dimensions exist on scales so small, smaller than an atom or proton, that they evade detection, yet they are crucial for the mathematical consistency of the theory. The existence of these hidden dimensions is essential for the strings to vibrate in a way that accounts for the particles and forces that shape our reality. Moreover, string theory has profound implications for understanding some of the most perplexing phenomena in physics, such as dark matter, dark energy, and gravity. The nature of these mysteries has long puzzled scientists, and higher dimensions may offer the key to unraveling them. For instance, the apparent weakness of gravity compared to the other fundamental forces might be explained if gravity is leaking into or interacting with other dimensions that we cannot directly perceive. While string theory is still very much a hypothesis, its potential to answer some of the most pressing questions in physics keeps it at the forefront of scientific inquiry. The search for experimental evidence to support or refute the existence of these additional dimensions is ongoing, with researchers employing cutting-edge techniques in particle physics and cosmology to probe deeper into the fabric of reality. Even further down this theoretical path lies M-theory, an extension of string theory that attempts to unite different versions of string theory into a single, cohesive framework. M-theory posits that our universe is made up of 11 dimensions. Like string theory, M-theory proposes that these additional dimensions are compactified and hidden from our direct view, but they play a crucial role in shaping the universe's structure. M-theory builds upon string theory's foundation that all matter and energy are composed of minuscule, vibrating strings, and aims to provide a unified description of all the fundamental forces and particles in nature, including gravity. In this way, M-theory holds the promise of bridging two of the most successful theories in physics, general relativity and quantum mechanics, which have, until now, seemed incompatible. General relativity explains the behavior of large-scale cosmic phenomena, like the motion of planets and the curvature of space-time around massive objects, while quantum mechanics governs the behavior of the smallest particles at the atomic and subatomic level. By incorporating higher dimensions, M-theory seeks to reconcile these two descriptions of the universe into one unified framework that can explain everything, from the smallest particles to the largest cosmic structures. However, just like string theory, M-theory remains a highly speculative idea. There is as yet no experimental evidence to confirm the existence of these extra dimensions, and some scientists remain skeptical about the theory's validity. Nevertheless, it continues to inspire new ways of thinking about the universe, offering a glimpse into a reality far more intricate than the one we perceive with our senses. The notion of higher dimensions also presents a challenge to our intuition, pushing the boundaries of human understanding. To explore spaces beyond our physical experience, mathematicians extend the principles of geometry and algebra into higher dimensions. Just as we use 3 coordinates to specify a location in 3-dimensional space, mathematicians use additional coordinates to define positions in spaces with 4, 5, or more dimensions. Each extra coordinate represents a new direction that is perpendicular to all the others, expanding the ways in which we can define spatial locations. Since we cannot directly experience higher dimensional spaces, mathematicians often rely on analogies to build intuition. They might ask us to imagine how a two-dimensional being would perceive a three-dimensional object passing through its world. By extending this idea, we can attempt to visualize what it might be like for us to glimpse a four-dimensional object within our three-dimensional reality, though such concepts remain firmly outside our direct experience. These abstract exercises provide a way to expand our thinking, allowing us to grapple with concepts that transcend the limitations of our senses. To aid in the study of higher dimensional spaces, mathematicians employ advanced tools like linear algebra and tensor calculus. These mathematical techniques allow them to manipulate complex, multi-dimensional structures, uncovering patterns and relationships that may have important applications in fields ranging from physics to computer science. These higher dimensional spaces are not just theoretical curiosities. They hold the potential for new insights into the fabric of reality and the forces that shape our universe. A hypercube, an abstract and captivating geometric concept, pushes the boundaries of our understanding of space and dimensions, extending the familiar structure of a cube into higher dimensional realms. While we are familiar with cubes in our three-dimensional world, the hypercube exists in a dimension beyond that, a realm that cannot be physically experienced in the same way we navigate the three-dimensional world we inhabit. The journey to understanding a hypercube begins with something far simpler, yet equally profound: a point. A point, in its most fundamental form, is zero-dimensional, offering no length, width, or depth. From this point, we can conceptualize the creation of a one-dimensional line by simply extending the point in a single direction. Next, by stretching this line perpendicularly to itself, we form a two-dimensional square. Continuing this progression, the square can be extended upwards, resulting in the three-dimensional cube. Each step introduces a new level of complexity, a deeper interaction with space itself. But what happens when we extend this process into the fourth dimension? Enter the hypercube, sometimes known as a tesseract in 4 dimensions. Imagine a cube but stretched into an additional dimension. In this higher dimensional space, the hypercube possesses 16 vertices, 32 edges, and 24 faces, a geometric complexity that far surpasses the simplicity of the three-dimensional cube. While this concept is challenging to visualize in our three-dimensional world, it serves as an invaluable tool for mathematicians and physicists. Hypercubes allow us to conceptualize and explore spaces that extend beyond the limits of everyday experience. These higher dimensional objects are not mere curiosities of geometry. They are vital for understanding the fundamental structure of the universe itself. The concept of a hypercube is not just an intellectual exercise, it is central to a wide range of scientific theories, from quantum mechanics to string theory. The very nature of our universe might depend on dimensions beyond the 3 spatial ones we observe daily. The exploration of these higher dimensions through the hypercube offers a window into the possible realities that govern the cosmos. Some physicists hypothesize that the universe has additional spatial dimensions that could help explain mysteries such as dark matter, the forces of gravity, or even the nature of time itself. By extending the familiar three-dimensional world into these uncharted territories, the hypercube becomes a bridge, a conceptual tool that helps us make sense of the invisible aspects of the universe. In a 4-dimensional space, the relationships between vertices, edges, and faces become increasingly complex. The hypercube, or tesseract, serves as a model for understanding how objects might behave in a universe with more than 3 spatial dimensions. These models are essential when theorizing about phenomena that cannot be observed directly, but may have significant implications for fields like particle physics and cosmology. The complexity of a hypercube parallels the complexity of space itself, especially as scientists continue to probe the possibility of more than 3 spatial dimensions. Though we cannot physically perceive a 4-dimensional object like the hypercube, we can make sense of it using various mathematical techniques. One common method is to consider lower dimensional analogies. For instance, imagine a 2-dimensional being living on a flat plane. This being could only perceive objects that existed within its 2-dimensional world. If a 3-dimensional object, like a sphere, passed through the plane, the 2-dimensional being would not see the sphere as a whole, but would only experience a series of cross-sections. As the sphere passed through, it would appear as a series of changing shapes, a slice of the whole object at each moment. Similarly, we can imagine how a four-dimensional object like a hypercube might appear to us in three-dimensional space. Just as the two-dimensional being perceives only cross-sections of a three-dimensional object, we would perceive a hypercube as a changing sequence of three-dimensional shapes. Mathematicians and physicists use projections and slices to represent four-dimensional objects in three dimensions. This technique is analogous to casting shadows. Just as a three-dimensional object casts a two-dimensional shadow, we can imagine a four-dimensional object casting a three-dimensional shadow. These projections provide a way to study and understand higher-dimensional objects, even though we cannot directly visualize them. While we may never fully grasp the reality of higher-dimensional spaces, mathematical tools and analogies allow us to develop theories that describe how such dimensions might function. The study of higher dimensional objects, such as the hypercube, has far-reaching applications in science and technology. In the realm of computer graphics, for example, hypercubes are used to model complex systems, representing multidimensional data in a way that is easy for humans to understand. In physics, hypercubes and higher dimensional spaces play a crucial role in the development of theories like string theory. String theory, which proposes that the fundamental building blocks of the universe are not point particles but tiny vibrating strings, relies on the existence of extra dimensions. These dimensions are theorized to be compactified, curled up so tightly that they are impossible to detect with current technology. Yet, the mathematical structure of string theory requires these extra dimensions to reconcile the laws of quantum mechanics with those of gravity, potentially offering a unified framework for understanding all forces in the universe. String theory proposes that the universe contains 10 or 11 dimensions, with the extra dimensions beyond the three spatial ones we observe potentially hidden from view. The shapes of these dimensions are theorized to be extraordinarily small, curled up at the Planck scale, so tiny that they are beyond the reach of current experimental tools. This idea raises tantalizing questions about the true nature of reality. Why don't we observe these additional dimensions in our everyday lives? Could they be detectable in some way if only we had the right tools to probe the universe at the smallest scales? These are the questions that drive much of the research in theoretical physics today. Experimental evidence for the existence of extra dimensions remains elusive. However, some phenomena, such as the behavior of gravity at very small scales, hint at the possibility that gravity might be leaking into these hidden dimensions. If this were true, it could explain why gravity is weaker than the other fundamental forces. It might be spreading out into additional dimensions, diluting its strength in our familiar three-dimensional space. To test these theories, scientists are using powerful particle accelerators, such as the Large Hadron Collider, LHC, to probe the fundamental structure of matter and energy. These accelerators smash particles together at incredibly high speeds, recreating conditions similar to those that existed in the very early moments of the universe. As particles collide, they produce a wealth of information that can help scientists understand the behavior of matter at the smallest scales, potentially offering clues about the existence of extra dimensions. One of the most exciting prospects is the idea that the creation of microscopic black holes could provide evidence for the existence of extra dimensions. If extra dimensions exist, the immense energy produced by particle collisions could be enough to produce tiny black holes, which would behave according to the laws of higher dimensional physics. Researchers are also searching for the elusive gravitons, hypothetical particles that mediate the force of gravity. If these particles exist and interact with extra dimensions, their properties could reveal much about the dimensional structure of the universe. The discovery of the Higgs boson in 2012 at the LHC was a significant milestone in our understanding of the universe. This particle, which gives mass to other particles, is a cornerstone of the standard model of particle physics. Yet its relatively low mass raises interesting questions. Some theories suggest that the Higgs boson's mass could be explained by the existence of extra dimensions. These dimensions could be affecting the behavior of the Higgs field, altering its properties in ways that are not yet fully understood. As particle accelerators continue to explore the fundamental nature of matter, they may provide further evidence that our universe is far more complex than we can currently perceive. By pushing the limits of experimentation and theory, scientists are gradually uncovering the secrets of the universe's hidden dimensions. Whether through the study of hypercubes, the development of string theory, or the search for experimental evidence, the quest to understand higher dimensions continues to drive innovation in both physics and mathematics. As we stretch our minds to comprehend these abstract and complex ideas, we open ourselves to a richer, more profound understanding of the universe and our place within it. Through the lens of higher dimensional geometry, we are not just looking at shapes and numbers, we are looking at the very fabric of reality itself. The discovery of the Higgs boson has opened up new and exciting avenues of exploration in fundamental physics, reigniting interest in supersymmetry, a theory that posits a partner particle for every known particle in the Standard Model. Supersymmetry is often coupled with string theory, which suggests that there are multiple hidden dimensions beyond our familiar three spatial dimensions and one time dimension. The ongoing search for supersymmetric particles could potentially provide strong evidence for these extra dimensions, offering a glimpse into a reality far beyond what we perceive. The Higgs boson plays an equally significant role in theories of quantum gravity, which aim to reconcile the two pillars of modern physics, general relativity and quantum mechanics. One such theory, loop quantum gravity, explores the possibility that space itself may be quantized at incredibly small scales, perhaps revealing additional dimensions or altering the geometry of space at the quantum level. In this context, the Higgs boson's properties could serve as a valuable tool in understanding the structure of space-time at these fundamental scales, guiding us toward a deeper understanding of dimensional theories and the universe's underlying architecture. One of the most fascinating connections between the search for extra dimensions and the fabric of reality is found in the study of gravitational waves. These ripples in space-time, first predicted by Albert Einstein and later detected by observatories, offer a unique opportunity to probe the very structure of the universe. While we typically experience the universe through three spatial dimensions and one time dimension, some theories, such as string theory, propose the existence of additional spatial dimensions. These extra dimensions might be compacted and invisible to our daily observations, yet they could interact with gravitational waves in ways that might one day be detectable by our instruments. If higher dimensions exist, gravitational waves could behave differently from our expectations in a four-dimensional universe, potentially propagating through these hidden dimensions and leading to subtle variations in their strength or frequency. The possibility that gravitational waves might interact with these extra dimensions is more than theoretical. Scientists are actively searching for anomalies in gravitational wave data that could provide indirect evidence for their existence. If such anomalies are found, they could reveal significant insights into the fundamental nature of gravity and space-time itself. Some models suggest that gravity may be stronger in higher dimensions, but it only appears weak in our observable universe. Gravitational waves could offer a means to test this hypothesis, potentially shedding new light on the invisible forces that shape the universe and its structure. At cosmic scales, several astronomical observations have raised intriguing questions about the nature of gravity and the possibility of extra dimensions. For instance, scientists have observed that gravity behaves differently at extremely large distances than what current models predict. This discrepancy could be explained by the existence of extra dimensions, where gravity leaks into these additional dimensions, weakening its force over vast distances. Such findings have prompted further exploration into the connection between gravity and higher dimensional theories, suggesting that the true nature of gravity may be far more complex than we currently understand. Another key observation supporting the concept of extra dimensions is the accelerating expansion of the universe. Rather than slowing down, as would be expected from gravitational attraction alone, the universe is expanding at an ever-increasing rate. This observation led to the hypothesis of dark energy, a mysterious force that could be influencing the universe's expansion. Some theories propose that dark energy might be the result of gravity interacting with hidden dimensions, subtly affecting the behavior of our visible universe in ways we cannot yet fully comprehend. Additionally, the study of cosmic inflation, the rapid expansion of the universe during its earliest moments, suggests that extra dimensions might play a crucial role in explaining the uniformity and flatness of the observable universe. Certain inflationary models that incorporate additional spatial dimensions can make predictions about the cosmic microwave background radiation, which align remarkably well with current observations. Although these observations do not provide definitive proof of extra dimensions, they present tantalizing clues that continue to inspire research in both theoretical physics and cosmology. As our observational technologies and techniques improve, scientists are hopeful that they will uncover more concrete evidence that could reveal the true nature of the universe and possibly confirm the existence of dimensions beyond the four that define our everyday experience. The study of dark matter has also intersected with theories involving higher dimensions, offering fascinating potential solutions to some of the universe's deepest mysteries. Dark matter, which does not emit, absorb, or reflect light, has long puzzled scientists because it does not behave according to the known laws of physics in the three-dimensional world. This has led some researchers to consider the possibility that dark matter might be influenced by, or even originate from, higher dimensions. According to string theory, the universe could have as many as 11 dimensions, and dark matter particles might be manifestations of tiny strings vibrating in these hidden dimensions. These higher dimensional interactions could explain why dark matter interacts so weakly with ordinary matter. Its gravitational effects might be spread across dimensions that we cannot directly observe, making it difficult to detect through traditional means. Another intriguing possibility comes from the concept of brain worlds, in which our observable universe exists on a three-dimensional membrane, a brain, floating within a higher dimensional space. In such models, dark matter could be regular matter trapped on a parallel brain, explaining its gravitational influence on our universe, while accounting for its apparent invisibility. These higher dimensional models offer potential solutions to some of cosmology's greatest challenges, such as understanding the distribution of dark matter in galactic halos, its role in large-scale cosmic structure formation, and its abundance throughout the universe. As dark matter detectors grow more sensitive and particle accelerators probe higher energies, scientists hope to find evidence that could either confirm or refute these higher dimensional theories. Such breakthroughs could revolutionize our understanding of the cosmos and the forces that shape it. Mathematical theories, such as string theory, suggest that the universe may be far more complex than our everyday experience implies. String theory, which seeks to unify the fundamental forces of nature, relies on the existence of 10 or 11 dimensions. These additional dimensions are thought to be tightly compacted, making them imperceptible at our scale. However, their existence is essential for maintaining the mathematical consistency of the theory. Other frameworks, such as the Kaluza-Klein theory, have also explored higher dimensional spaces. While the Kaluza-Klein theory was not fully successful in unifying gravity with electromagnetism, it provided an early glimpse into how additional dimensions might explain fundamental forces in our universe. Mathematicians have also explored higher dimensional analogs of familiar geometric objects, such as polytopes in 4 dimensions. These abstract mathematical structures cannot exist within our three-dimensional space, but they offer intriguing possibilities for the rich complexity that additional dimensions could introduce. Even quantum mechanics, which underpins much of modern physics, provides indirect support for the idea of higher dimensions. The mathematical formalism of quantum theory often involves multidimensional Hilbert spaces, hinting that the true nature of reality may be far more intricate than our limited perception suggests. One of the most compelling pieces of evidence for higher dimensions comes from the counterintuitive behavior of quantum particles in experiments like the double-slit experiment. In this experiment, particles such as electrons or photons are fired through two narrow slits and detected on the other side. Classical physics predicts that these particles should create two distinct bands on a detector. However, what is observed is an interference pattern, suggesting that each particle has passed through both slits simultaneously, a phenomenon known as quantum superposition. This strange behavior challenges our understanding of reality, and some theorists propose that extra dimensions might offer an explanation, allowing particles to interact with or travel through these additional dimensions in ways we cannot observe. Quantum entanglement, another puzzling quantum phenomenon where particles instantaneously affect each other regardless of distance, further fuels the idea that hidden dimensions could be at play. These extra dimensions could potentially explain how information or influence can travel faster than the speed of light without violating the principles of relativity. Although these ideas remain speculative, they push the boundaries of our understanding and suggest that the universe is far more complex and mysterious than we can fully grasp. In the quest to unify the fundamental forces of nature and unlock the mysteries of the universe, higher dimensions remain a crucial piece of the puzzle. As research in theoretical physics, cosmology, and quantum mechanics continues to evolve, the potential for discovering evidence of additional dimensions, whether through gravitational waves, dark matter, or quantum phenomena, remains one of the most exciting frontiers of scientific inquiry. These additional spatial dimensions, which extend beyond the three that define our daily experiences, open up a remarkable potential framework for reconciling the forces of nature, bridging the gap between gravity and the other fundamental forces. Electromagnetism, the strong nuclear force, and the weak nuclear force all behave differently, yet they are ultimately manifestations of the same underlying principles. String theory, one of the leading candidates for a unified theory of physics, proposes that our universe is much more complex than it appears. In this framework, the universe is believed to contain 10 or 11 dimensions, far beyond the three spatial dimensions and one time dimension that we can observe. These extra dimensions are not immediately apparent because they are theorized to be tightly curled up, incredibly compacted, and so small that they exist beyond the reach of any current observational technology. This curling is so extreme that these dimensions do not interfere with the familiar physical world we experience. The proposal that extra dimensions exist offers a compelling solution to one of the deepest questions in physics. How can gravity, the weakest of the four fundamental forces, be reconciled with the stronger forces that govern subatomic particles? In string theory, these compact dimensions provide the necessary mathematical space for gravity to engage in interactions with the other forces, giving them a shared stage. This model holds promise for a more symmetric and elegant framework that could explain the universe in a unified way. Through this lens, the seemingly arbitrary properties of particles, such as their masses and electric charges, could actually emerge from the way the fundamental strings that make up matter vibrate in these hidden dimensions. As these strings oscillate, they generate the characteristics we observe in particles, providing a new way to understand the properties of matter. The potential of higher dimensions is not just theoretical, but practical, offering possible answers to long-standing puzzles in physics. Among these is the hierarchy problem, which questions why gravity is so much weaker than the other forces. By expanding our understanding of the dimensions beyond our perception, these extra spatial dimensions could allow gravity to be more integrated with the stronger forces, possibly explaining its relative weakness. Additionally, theories of higher dimensions might also hold the key to unlocking the mysteries of dark matter, that invisible substance believed to account for a large portion of the mass in the universe, and dark energy, the mysterious force driving the accelerated expansion of the cosmos. While the existence of higher dimensions remains hypothetical, the theoretical implications of their presence are incredibly stimulating, inspiring a vast amount of research in both particle physics and cosmology. Physicists are exploring various ways to indirectly detect evidence of these hidden dimensions, and any such discovery could revolutionize our understanding of the universe. It could provide us with the missing link in the quest for a theory of everything, a unified theory that ties together all fundamental forces of nature, including gravity. At the same time, supersymmetry, another captivating concept in theoretical physics, seeks to build on the idea of these higher dimensions. Supersymmetry posits a deep connection between two different categories of particles: bosons, which carry forces, and fermions, which make up matter. According to this theory, every known particle has a supersymmetric partner that mirrors its properties but differs in terms of its spin. This radical symmetry between particles has far-reaching implications for how we understand the fundamental building blocks of the universe. The link between supersymmetry and higher dimensions becomes clearer when string theory is introduced. String theory, a leading candidate for unifying the forces of nature, requires the existence of extra-spatial dimensions. These dimensions, which are tightly compacted and beyond our perception, could provide the necessary space for supersymmetric particles to exist. In certain versions of string theory, supersymmetry is not just a possibility, but an inevitable outcome of the extra dimensions. As we move through higher dimensional space, new symmetries emerge, including the intriguing symmetry between bosons and fermions. This idea suggests that the extra dimensions could be instrumental in explaining why the universe exhibits the properties it does. Even though supersymmetry and higher dimensions remain speculative, they offer tantalizing clues about the fundamental nature of reality. Both concepts challenge our understanding of the universe and push the boundaries of physics. Scientists continue to look for signs of supersymmetric particles and indirect evidence of extra dimensions, hoping that these elusive discoveries could shed new light on the deepest mysteries of the cosmos. One particularly provocative concept that has emerged from modern physics is the holographic principle, which suggests that our perception of three-dimensional reality could be an illusion. The principle posits that all the information contained within a region of space can be described by the information on the two-dimensional boundary of that region. This notion draws a fascinating parallel to the idea of a hologram, where a three-dimensional image is encoded on a two-dimensional surface. The holographic principle suggests that what we experience as three-dimensional space could, in fact, be a projection of information that exists on a lower dimensional boundary. In other words, the universe as we know it might be a vast hologram, with our reality emerging from a two-dimensional cosmic surface. This radical idea has profound consequences for how we think about the nature of space, time, and reality itself. It challenges our deeply ingrained intuition that space is three-dimensional and suggests that the very fabric of the cosmos may be far more abstract than we realize. The implications of the holographic principle extend into quantum gravity, black hole physics, and our understanding of how fundamental forces work. It has led physicists to explore the possibility that the universe itself might be a projection, encoded on some distant, faraway surface. This idea continues to inspire new research and could reshape how we think about the fundamental structure of the universe. In the search for a unified theory of quantum gravity, theories that incorporate higher dimensions play a pivotal role in extending our understanding of space and time. One of the most prominent frameworks, string theory, requires the existence of 10 or 11 dimensions to explain the behavior of the fundamental forces and particles in nature. These extra dimensions, though unseen by our current instruments, are essential for the mathematical formulation of the theory, with string-like objects vibrating in these higher dimensional spaces to manifest as particles in the familiar three-dimensional world. This framework holds promise in its potential to reconcile quantum mechanics with general relativity, offering a unified description of all forces and particles. An alternative approach, known as loop quantum gravity, challenges the need for extra dimensions, but presents a new perspective on space and time at the quantum level. It suggests that space itself is made up of discrete units, tiny, indivisible atoms of geometry, an idea that becomes evident only at the smallest scales. This view of space as granular at the quantum level has intriguing implications for our understanding of the universe. Whether through higher dimensions or granular geometry, both string theory and loop quantum gravity attempt to explain the fundamental forces and particles in a unified framework, holding the potential to unlock mysteries such as dark matter, dark energy and black hole singularities. Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xingteng Yau, are central to string theory as they represent the hidden dimensions that lie beyond our perception. These complex geometric structures provide a mathematical framework for understanding the shape and size of the curled-up dimensions that string theory predicts. The shape and configuration of these Calabi-Yau manifolds have profound consequences for the properties of the universe. They dictate the types of particles that exist and the forces that govern their interactions. In essence, the specific geometry of these manifolds could define the very laws of physics in our universe, and different shapes could give rise to entirely different universes with their own unique sets of physical laws. Although these ideas remain theoretical, they offer a fascinating glimpse into the possible architecture of reality. The study of Calabi-Yau manifolds has become a crucial part of the quest for a unified theory of physics, driving forward the investigation into how the fundamental forces of nature are interconnected. Understanding these complex structures is key to the ambition of string theorists to unify quantum mechanics and general relativity, providing a coherent framework for all of physics. Finally, the hierarchy problem, one of the most perplexing issues in modern physics, highlights the extraordinary discrepancy between the strength of gravity and the other fundamental forces. Gravity, despite its ubiquitous presence, is vastly weaker than the electromagnetic force and the nuclear forces, a discrepancy that has puzzled scientists for years. The existence of extra dimensions could offer a solution by suggesting that gravity is not inherently weak, but instead is diluted across multiple dimensions, becoming less apparent in our three-dimensional world. This idea proposes that gravity might in fact be just as strong as the other forces, but its effects are spread out in ways that are not immediately noticeable in our everyday experience. In exploring these cutting-edge theories, physicists are pushing the boundaries of what we know about the universe. From supersymmetry to string theory, holography, and the intricate structures of Calabi-Yau manifolds, the search for a unified theory of everything is one of the most exciting frontiers in science today. As new discoveries unfold, they promise to reshape our understanding of the cosmos, revealing a deeper and more intricate structure to the reality we thought we knew. Gravity, one of the most familiar forces in the universe, might not be as weak as we think. In fact, according to certain theories that involve extra dimensions, gravity could be just as strong as the other fundamental forces, but the majority of its strength is leaking into hidden dimensions that we cannot perceive. This suggests that the gravity we experience in our observable universe is only a fraction of its true power. The idea behind this is intriguing. While forces like electromagnetism, the strong force, and the weak force are confined to the three spatial dimensions we experience, gravity, by contrast, may be able to spread out across all dimensions, including these extra ones that remain beyond our detection. These hidden dimensions are theorized to be incredibly small and curled up, so small, in fact, that they exist on scales far smaller than an atomic nucleus, which is why we have not been able to detect them directly with current observational methods. The existence of such dimensions provides a potential explanation for why gravity appears so weak when compared to other forces. If gravity were able to interact across multiple dimensions, its influence could be diffused over these extra spatial realms, making its effects seem diminished in our three-dimensional world. This elegant solution could, in theory, reconcile the hierarchy problem, why gravity is so weak compared to other forces, and bring about a long-sought unification of the fundamental forces. If proven true, this idea could revolutionize our understanding of the universe, and perhaps provide the key to linking gravity with the other forces of nature, a challenge that has remained elusive for generations of physicists. However, despite its elegant theoretical appeal, this notion of extra dimensions remains speculative. The evidence for these hidden dimensions is still elusive, and the search for direct proof continues to be an area of intense scientific inquiry. But the very possibility of extra dimensions adds an exciting layer of complexity to our understanding of reality. Equally captivating is the concept of brain theory, a fascinating idea in theoretical physics that expands our view of the universe beyond the familiar dimensions of space and time. The term brain is short for membrane, and this theory suggests that our entire universe might be a three-dimensional brain floating within a higher dimensional space. In this framework, our universe is just one of many possible brains that could exist in a vast multiverse. These brains, existing in higher dimensional space, could be separated by incredibly small distances, which are imperceptible to our senses. If this is the case, it would mean that there might be other universes, perhaps similar to our own, lying just out of reach in these hidden dimensions. This theory provides an elegant explanation for why gravity appears weaker than other forces. It proposes that gravity, unlike the other forces, is not confined to our three-dimensional brain. Instead, it is free to spread its influence across the higher dimensional space in which these brains exist. This could help to explain some of the universe's greatest mysteries, such as the nature of dark matter or why gravity seems to be so much weaker than electromagnetic forces. According to brain theory, while we are confined to our three-dimensional universe, gravity and potentially other forces could interact across the boundaries of these extra dimensions, leading to the dilution of gravity's strength in our observable universe. The idea of brains, higher dimensions, and the multiverse challenges our everyday understanding of reality. It suggests that the universe we observe may be only a small piece of a much larger, far more intricate cosmic structure. This notion resonates with the theory of the multiverse, where our universe exists as just one of many parallel universes, each potentially operating according to different physical laws or constants. In this scenario, other universes might exist on different branes, separated by dimensions we are incapable of perceiving. This model might explain why gravity is so comparatively weak. Its influence could be spread out across the higher dimensional space, interacting with other universes in ways that we cannot yet fully comprehend. In addition to the brain theory, there is another multiverse model known as the many worlds interpretation of quantum mechanics. This theory takes a different approach and does not necessarily rely on extra dimensions. Instead, it suggests that every quantum event results in the splitting of reality, creating new branches of the timeline and effectively new universes. While this interpretation does not explicitly invoke higher spatial dimensions, it aligns with the idea of a far more complex and multi-layered reality than we typically experience. Both the brain theory and the many worlds interpretation challenge our intuitive understanding of the universe, expanding the limits of what we consider possible and offering intriguing new ways to think about the nature of existence. One of the most profound implications of theories involving higher dimensions is their potential to radically alter our conception of reality. We live in a world where our everyday experience is confined to three spatial dimensions and one dimension of time. Yet, theoretical physics and advanced mathematics suggest the existence of additional dimensions beyond these. These extra dimensions are, by definition, outside the range of our direct sensory perception, because we cannot see, touch, or interact with them in the same way we do with the familiar dimensions of length, width, and height. This creates a fundamental challenge in grasping their true nature. To illustrate, imagine a two-dimensional being living on a flat surface. This being would have no way of perceiving depth. Similarly, we as three-dimensional creatures in life find it difficult to comprehend higher dimensional space, which remains beyond the reach of our senses. Despite this challenge, higher dimensions could offer solutions to some of the most puzzling phenomena in physics, such as quantum entanglement or the mystery of dark matter. The suggestion that there could be hidden dimensions in which forces like gravity are more powerful than we realize opens up new avenues for explaining the forces at play in the cosmos. Higher dimensions also challenge our notions of causality, time, and the very structure of the universe. They invite us to reconsider everything we know about the universe, suggesting that what we perceive as reality is merely a small portion of something much more vast and intricate. The concept of higher dimensions extends beyond mere theoretical physics and touches on profound philosophical questions. Could our understanding of the universe be inherently limited by our inability to directly experience dimensions beyond the three we know? Are there aspects of existence that will forever lie beyond our comprehension? Another deep question raised by the existence of higher dimensions is the nature of consciousness itself. Could human awareness be influenced by or even derived from these higher dimensional realms? This inquiry invites speculation on the very essence of human consciousness and its relationship to the cosmos. Additionally, the existence of higher dimensions raises important questions about the nature of free will and causality. If the events that unfold in our three-dimensional world are influenced by forces or entities in higher dimensions, it could reshape our understanding of cause and effect. It might even challenge the degree to which we can control our actions and decisions, forcing us to reconsider our fundamental assumptions about free will. Furthermore, if the laws of physics are not the final word, but are merely shadows of deeper, more complex principles operating in higher dimensions, it could force us to rethink the very nature of reality and the limits of human knowledge. Are we on the verge of discovering a deeper truth that lies beyond our current understanding, or are we limited by the bounds of our perception, forever confined to the familiar dimensions we can perceive? The concept of higher dimensions pushes us to ask such questions and challenges our deepest beliefs about existence, knowledge, and the cosmos itself. If we delve into the notion of higher dimensions beyond our observable reality, it's easy to imagine how this could dramatically alter our understanding of free will. Our perception of free will, rooted in our three-dimensional experience, may seem entirely self-contained, yet the existence of higher dimensions could reveal a vastly different narrative. In our limited three-dimensional world, events and choices often appear disconnected, unfolding in a linear fashion with a clear cause and effect. However, when viewed from a higher dimensional framework, these same events may be intricately interwoven, revealing a tapestry of causality that stretches far beyond our ability to perceive. This new vantage point could suggest that what we perceive as independent choices, free will itself, might not be as autonomous as we believe. Instead, these choices could be part of a larger predetermined pattern that remains hidden to us due to our dimensional limitations. In such a model, our conscious minds may not be isolated to just the three spatial dimensions and one temporal dimension we know. Perhaps our consciousness extends into higher dimensions, influencing and being influenced by realms of existence we cannot directly access. This idea opens up the possibility that our decision-making processes could transcend the boundaries of physics and neuroscience as we understand them today. It suggests that free will might not merely be a product of neurons firing in a linear physical space, but instead could be influenced by forces from higher dimensions, forces that shape and guide our choices in ways our three-dimensional minds cannot fully grasp. The implications for our understanding of causality are profound. We are accustomed to thinking of cause and effect in a straightforward manner. In our world, an action leads to a direct consequence, and that consequence, in turn, leads to further actions. However, in higher dimensions, the relationship between cause and effect could be far more intricate. The events we observe as unrelated might be part of a single, unified phenomenon, governed by principles of causality that operate beyond the familiar rules of time and space. Consider the experience of a two-dimensional being encountering a three-dimensional object. From their perspective, the object would appear in disconnected fragments, perhaps as a simple circle that changes shape and disappears without apparent reason. What they fail to understand, due to their dimensional constraints, is that the object is in fact a full three-dimensional form, which they can only perceive in limited slices. Similarly, in higher dimensions, our perception of separate events could be the result of our inability to see the underlying unity that connects them. This shift in perspective allows for the possibility that distant points in space and time could be naturally linked through the higher dimensions, even though we perceive them as isolated. It opens the door to explaining otherwise puzzling phenomena, such as quantum entanglement, where particles influence one another instantaneously across vast distances. These events defy our current understanding of physics, yet might be entirely normal when viewed from a higher dimensional standpoint. Moreover, this concept suggests that time itself, an abstract but fundamental element of our reality, could behave in ways we are not equipped to understand from our current vantage point. Even more intriguing are the possibilities of higher dimensional causality. Events may no longer be confined to the familiar linear chain of cause and effect. Instead, actions could ripple through the hidden dimensions, creating causal connections that seem to defy our current understanding of physics. The implications of such a framework could revolutionize fields such as theoretical physics and cosmology, providing new ways to explore the deepest mysteries of the universe and its fundamental workings. This framework also intertwines with concepts of determinism, suggesting that the universe might be a deterministic system, with all events and choices predestined by prior causes. If higher dimensions encode all possible outcomes, our observable universe might represent only a single trajectory through an infinitely complex landscape of possibilities. From this perspective, free will may be an illusion, and what we experience as choice could simply be the result of following a path laid out by forces beyond our comprehension. The phenomenon of quantum mechanics further complicates our understanding of determinism. At first glance, quantum particles behave in ways that seem entirely random and unpredictable. However, some theories suggest that, when viewed from a higher dimensional perspective, these seemingly random behaviors could be fully deterministic. This means that what we perceive as randomness or freedom of choice might simply be the result of our inability to perceive the full range of factors influencing an event. Of course, these ideas remain speculative. While higher dimensional models serve as powerful tools in theoretical physics, their direct connection to determinism or the nature of reality is still a matter of philosophical debate. What these models offer, however, is an exciting glimpse into a new framework that could one day transform our understanding of everything from consciousness to the very fabric of the universe itself. Consciousness, one of the greatest enigmas in science, might also be explained in the context of higher dimensions. We experience our consciousness in a limited three-dimensional world, yet the mind may be a product of processes that extend far beyond our perceptual boundaries. The hard problem of consciousness, how subjective experiences arise from the physical interactions of neurons in the brain, could find new insight through the lens of higher dimensional models. These dimensions might provide a structure that accounts for how we experience consciousness, possibly even positioning our brains as mere receivers or interpreters of information from higher dimensional sources. This aligns with certain philosophical and spiritual views, which hold that consciousness is not an emergent property of the brain, but a fundamental aspect of the universe itself. In fact, higher dimensions could provide explanations for phenomena that currently elude scientific understanding. Near-death experiences, altered states of consciousness, and the sensation of unity in deep meditative states might all be framed in terms of higher dimensional interactions. These experiences, often dismissed as illusions or psychological phenomena, could instead reflect genuine access to higher realms of existence, realms that, while currently invisible to us, shape our experiences in profound ways. Expanding our understanding of dimensions beyond the familiar could potentially bridge the divide between the material world and the subjective experience of consciousness. Interestingly, the concept of higher dimensions is not a new one. Ancient civilizations and philosophical traditions have long speculated about the nature of reality and the possibility of realms beyond the one we experience. Plato's allegory of the cave, for instance, presents an image of people who, chained within a cave, can see only the shadows cast on a wall. They mistake these two-dimensional projections for the entirety of reality. This analogy mirrors our own situation as three-dimensional beings who are limited to perceiving only a fraction of a potentially much larger reality. In Eastern philosophies like Buddhism and Hinduism, there are references to multiple realms of existence, much like the extra dimensions proposed by string theory in modern physics. These ancient views are strikingly similar to contemporary scientific models, suggesting that our ancestors may have intuitively grasped concepts that modern physicists are only now beginning to explore. Moreover, the mystical tradition of Kabbalah presents a multi-layered view of reality, in which different levels of existence are intricately connected. This hierarchical structure of reality bears a remarkable resemblance to the way physicists describe relationships between dimensions. These philosophical and spiritual insights suggest that the questions we grapple with today about the nature of free will, consciousness, and the structure of the universe are not entirely new. They have been considered, in one form or another, for thousands of years. The potential existence of higher dimensions also carries profound ethical implications. If forces or entities from these dimensions can influence our universe, we must reconsider the very nature of free will and moral responsibility. Are our choices genuinely our own, or are they subtly shaped by unseen forces? If higher dimensional beings can interact with our world, how accountable are they for the outcomes of their actions? Furthermore, if our own choices are influenced by higher dimensional forces, what does this mean? What does this mean for our sense of moral responsibility? This potential also raises significant concerns about autonomy and privacy. If beings from higher dimensions can perceive or even interact with our world in ways beyond our detection, the very idea of personal freedom might be called into question. Could our actions, thoughts, or experiences be observed or manipulated by entities from other dimensions? This could lead to a new kind of cosmic surveillance, where every aspect of our existence is subject to influences beyond our comprehension. The very concept of privacy might need to be redefined if higher dimensional forces are involved in our lives in ways we cannot fathom. In the end, the existence of higher dimensions challenges not only our understanding of the physical world, but also the very core of our philosophical, ethical, and spiritual beliefs. It forces us to reconsider what we know about causality, free will, consciousness, and the nature of reality itself. While these ideas remain speculative, the very act of contemplating them pushes the boundaries of human thought, urging us to look beyond the limitations of our senses and explore the hidden depths of existence. As humanity continues to push the boundaries of our understanding, we are confronted with an immense ethical dilemma. How should we respond to the potential for higher dimensional influence? The possibility that entities from dimensions beyond our own may exist presents profound questions that we, as a species, must grapple with. Should we seek to understand and even communicate with these higher dimensional beings, or would such efforts be fraught with dangers that could expose our universe to risks we cannot yet fathom? This is not merely a scientific or philosophical issue, but one that forces us to examine the ethical frameworks that govern our actions, our responsibilities, and ultimately our place in an increasingly complex and mysterious cosmos. The potential for higher dimensional entities to influence our reality challenges our conceptions of life, the universe, and everything in between. Higher dimensional concepts have captured the human imagination for centuries, and they have profoundly influenced both literature and science fiction. These ideas allow writers to explore the unknown, intertwining complex scientific theories with captivating narratives that challenge our perceptions of what is real. One of the earliest works to explore higher dimensional ideas was Edwin Abbott's Flatland, a novella that introduced readers to a two-dimensional world and used it as a tool to explore how higher dimensions might interact with lower ones. Abbott's work is as much a social satire as it is a mathematical exploration, asking readers to consider how we perceive reality and whether there might be more to existence than meets the eye. The story of Flatland not only opens the door to thinking about dimensions beyond the three we experience, but it also serves as a metaphor for human tendencies to dismiss what is not immediately understandable. Other authors, such as H.G. Wells, expanded upon these ideas. His work, The Time Machine, introduced the concept of time as a fourth dimension, a groundbreaking notion that opened the floodgates for the exploration of time travel in science fiction. The idea that time is not simply a linear progression, but a spatial dimension that could be navigated radically, reshaped how we think about the passage of time and its connection to the physical world. Over time, the idea of higher dimensions has evolved from theoretical musings into a major motif in science fiction, especially in works involving parallel universes, alternate realities, and multidimensional travel. Authors like Isaac Asimov and Arthur C. Clarke pushed these boundaries further. Asimov's stories, deeply rooted in hard science, incorporate ideas about higher dimensions, often suggesting that the key to understanding the future of humanity lies in our ability to transcend our three-dimensional limitations. Clarke, on the other hand, embraced the mind-bending implications of higher dimensions, using them as tools for speculative fiction that stretches the imagination. In the visual realm, the concept of the hypercube or tesseract has become iconic, as it allows the representation of multiple dimensions in a form that humans can visualize. From the pages of M.C. Escher's intricate drawings to the cosmic spaces of Marvel's Doctor Strange, the Tesseract has provided a way to conceptualize the infinite and the unknown. The depiction of higher dimensional spaces allows for the creation of worlds and possibilities beyond the familiar, where anything seems possible, and the boundaries of reality are constantly shifting. This embrace of higher dimensional ideas has not been limited to the written word. It has extended into film, television, and other forms of media. One of the most notable cinematic explorations of higher dimensions is Interstellar, directed by Christopher Nolan. The film's portrayal of a tesseract, an abstract, multidimensional space where time is no longer linear but becomes a navigable entity, allowed audiences to imagine time not as a rigid progression, but as a fluid dimensional landscape that can be traversed. Interstellar captivated viewers by bringing the concept of higher dimensions into a narrative that blended emotional depth with theoretical physics, offering an accessible portrayal of otherwise incomprehensible scientific theories. Similarly, the iconic British TV series Doctor Who has long been a platform for exploring interdimensional travel. The TARDIS, the time-traveling machine that is larger on the inside, represents the notion that space and time are not bound by traditional three-dimensional constraints. In the Marvel Cinematic Universe, films like Doctor Strange explore these ideas visually, with the titular character manipulating reality and exploring other dimensions with kaleidoscopic effects that reflect the mind-expanding nature of the multiverse. These works of fiction have not just entertained audiences, they have also contributed significantly to the popularization of higher dimensional theories and the ideas of the multiverse, string theory, and quantum mechanics. The blending of science and fiction in these media representations helps make complex, abstract scientific ideas more accessible to a general audience, sparking curiosity and prompting questions about the fundamental nature of the universe. This intersection between science and imagination is no longer a one-way street. Scientific developments inspire fiction, and in turn, fiction fuels the public's appetite for more scientific inquiry. But higher dimensional concepts aren't confined to the realm of science fiction. Artists have long been drawn to these abstract ideas, seeking to express them visually. In the early 20th century, the Cubist movement, led by artists like Pablo Picasso, experimented with the idea of presenting multiple perspectives of a single object on a two-dimensional canvas. This technique, which allows the viewer to see all sides of a subject at once, hints at a fourth spatial dimension, suggesting that there might be more to reality than meets the eye. Similarly, M.C. Escher, the Dutch artist known for his impossible geometries, used his lithographs and woodcuts to play with concepts of higher dimensional space. Escher's intricate patterns and paradoxical structures challenge the viewer to stretch their understanding of what is physically possible, offering a visual representation of higher dimensional thinking that forces us to grapple with the concept of reality in new and unsettling ways. In more recent years, digital artists have used technology to explore these ideas further. Through computer graphics and advanced rendering techniques, they can create representations of higher dimensional objects, shapes that exist in more than 3 dimensions, but are projected into the 3-dimensional world. These creations, often shifting and morphing in ways that defy conventional geometry, allow viewers to engage with the unfamiliar and the unknown. Other artists have taken a more abstract approach, using concepts from string theory, quantum mechanics, and mathematics to create installations or sculptures that embody the principles of higher dimensions. These works attempt to make the intangible tangible, challenging us to rethink the nature of reality itself. The influence of higher dimensional thinking also extends to religious and spiritual beliefs. For many, the idea that our universe might contain more dimensions than the 4 we commonly experience offers a new way to think about God, the soul, and the afterlife. Higher dimensional theories present a framework in which spiritual realms might exist, offering a bridge between science and faith. Some believe that these additional dimensions could be home to spiritual entities or serve as the realm of the afterlife, providing a scientific grounding for beliefs that were once considered purely metaphysical. For others, however, these theories are not a solution, but rather a new complication. Critics argue that the invocation of higher dimensions to explain spiritual phenomena simply replaces one unknown with another. They contend that such theories lack concrete evidence, and instead of offering clarity, they introduce even more abstract questions that cannot be empirically tested. This ongoing dialogue between science and spirituality continues to evolve, shaping the way we think about existence, consciousness, and the universe. It encourages both believers and skeptics to reconsider their views on the nature of reality and to explore the intersections between the physical and the metaphysical. Just a century ago, the idea that science and spirituality could be so intertwined would have seemed impossible. Today, however, higher dimensional theories have blurred these lines, offering new perspectives that challenge both our scientific and spiritual paradigms. Beyond the realms of philosophy and theology, the concept of higher dimensions has influenced the field of music and sound art. Musicians and sound artists have drawn inspiration from theoretical physics to create compositions that stretch the boundaries of auditory perception. By using complex layering techniques and unconventional harmonies, composers create soundscapes that evoke the feeling of higher dimensional spaces, auditory environments that feel as though they exist beyond our traditional understanding of space. This innovative approach to sound challenges the listener to experience music not just as a sequence of notes, but as a spatial, dimensional experience that taps into the unknown. Through these compositions, artists attempt to represent the concept of higher dimensions, transforming abstract scientific ideas into an immersive auditory experience that expands our understanding of sound, space, and perception. Higher dimensional theories have not only reshaped the way we think about the universe, but have also opened up new avenues of creative exploration. From literature to art, science to religion, these ideas continue to push the limits of human understanding, offering fresh perspectives and sparking deep questions about reality, existence, and the possibilities that lie beyond our perception of the world. These artistic creations are often designed to offer listeners an experience that goes beyond the ordinary confines of our three-dimensional reality. At the heart of this work lies an effort to craft something that feels otherworldly, transcending the limits of physical space as we know it. Many musicians and sound artists have pushed boundaries by developing entirely new instruments or altering existing ones to produce sounds that feel like they belong to a different dimension. For instance, electronic music producers, with a firm grasp on the power of mathematics, frequently use algorithms grounded in higher dimensional concepts to create sounds that challenge our usual understanding of tone and rhythm. Their music doesn't merely inhabit the space around us, but seems to bend it, creating an auditory experience that surrounds and engulfs. Advanced audio technologies are often employed to further intensify this experience. High-quality, multi-dimensional speaker systems work in tandem with the sounds themselves, enveloping the listener and dissolving the boundaries between sound and space. This blend of auditory innovation and spatial awareness has led to a reimagining of how sound can influence our perceptions of reality. Artists now create conceptual works that don't just sit in the realm of sound, but intertwine with the very fabric of space and time. These works frequently feature visual elements, sometimes in the form of immersive, interactive installations, encouraging audiences to participate in ways that stretch their understanding of dimensionality and sensory perception. The creative world's journey into higher dimensions isn't just an exploration for artistic indulgence. It serves a deeper purpose, expanding our understanding of the universe itself. By pushing the limits of what is possible with sound, artists are unveiling new ways to perceive our place in the cosmos. Higher dimensions, once a purely theoretical idea, have now become a playground for digital artists, designers, and creators of virtual realities. With the tools of modern technology, these artists draw on abstract mathematical and physical principles to develop surreal visual experiences that make us question the limits of our existence. In the world of digital art, Artists are not merely creating aesthetically appealing works, they are making the invisible tangible. By simulating higher dimensional spaces, they give us a window into realms that exist only in abstract theories. These works often feature impossible geometries, strange non-Euclidean structures, and mind-bending visual paradoxes that challenge our senses and our ability to distinguish between reality and illusion. The manipulation of perspective, color, and form within these pieces doesn't just defy conventional physics, it offers viewers a glimpse into worlds that our minds can barely comprehend. Through software and algorithms, these digital creations simulate the vast, uncharted spaces that exist beyond the boundaries of our three-dimensional world. Virtual reality, VR, represents a significant leap forward in this journey. VR takes the exploration of higher dimensions to extraordinary new heights by allowing users to immerse themselves fully in virtual spaces that defy the rules of conventional physics. In these simulated environments, the ordinary laws of space break down, offering a visceral experience of what it might feel like to exist in a universe where more than 3 spatial dimensions exist. As users navigate these warped realities, they're not merely passive observers, but active participants, interacting with and altering their surroundings in ways that are simply impossible in the physical world. But the intersection of higher dimensions, digital art, and virtual reality goes beyond creative expression. It also serves as a vital educational tool, particularly in the realm of science and mathematics. The intangible nature of many complex mathematical concepts becomes more accessible when they are visualized and experienced interactively. For example, abstract notions in theoretical physics that are often difficult for the public to grasp can be rendered in fully immersive VR environments, making them easier to understand. These virtual spaces turn intricate ideas into something tangible, enabling learners and explorers alike to better comprehend the vastness and complexity of the universe. In addition to digital artists and scientists, game designers have also found ways to incorporate higher dimensional concepts into their work. These concepts have unlocked new and exciting possibilities in game design, introducing players to experiences that stretch the very boundaries of spatial reasoning. Some video games, such as Makur, allow players to navigate through a 4-dimensional world. In this game, the player must shift between different 3-dimensional cross-sections of this higher dimensional space to solve puzzles and navigate obstacles that would be impossible to traverse in our familiar 3-dimensional reality. Other games, like Portal and Antichamber, use principles like non-Euclidean geometry and interconnected portals to create mind-bending spaces that force players to rethink their understanding of space and movement. These games challenge players to engage with higher dimensional concepts in an interactive environment, often using objects such as tesseracts or hypercubes to deepen the puzzle's complexity. However, misconceptions about higher dimensions abound, especially when it comes to their role in popular culture. Many people mistakenly think of higher dimensions as mystical realms or parallel universes we could one day explore. While this idea is an enticing one for science fiction, it is not scientifically accurate. In reality, higher dimensions are mathematical constructs that help us describe the properties of space and time, not tangible places we can physically visit. Another misconception is that the 4th dimension is time. While time is often referred to as the 4th dimension in the context of physics, it is not the same as spatial dimensions. Time functions differently, and in mathematical terms, the 4th dimension is simply an additional spatial direction that is perpendicular to the 3 we experience. Further misunderstandings arise from the belief that beings in higher dimensions would have godlike abilities, able to manipulate our 3-dimensional world at will. This misunderstanding stems from a basic confusion about how dimensional relationships function. A 4-dimensional being would not perceive our world any more uniquely than we do. In fact, they would likely have their own version of dimensional blindness when interacting with our 3-dimensional space. A particularly prevalent myth is the belief that string theory proves the existence of higher dimensions. While string theory does propose the existence of additional dimensions, these dimensions are not vast expanses that we could visit. Rather, they are incredibly small and curled up in ways that make them imperceptible to our senses. These misconceptions highlight the immense challenge of communicating the true nature of higher dimensions to the public. Despite the misunderstandings surrounding them, higher dimensions continue to captivate the imagination of scientists and artists alike. Their potential influence on our three-dimensional reality is still a topic of much speculation in the field of theoretical physics. Some scientists theorize that higher dimensions may exert influence over our world through gravity, which behaves differently than other fundamental forces. Gravity, they suggest, could spread out across multiple dimensions, which might explain why it appears weaker compared to other forces like electromagnetism. Other theories propose that higher dimensions could harbor vast amounts of energy or exotic matter, influencing the behavior and structure of our universe. It is even speculated that these hidden dimensions could play a role in the distribution of dark matter and dark energy, which together account for approximately 95% of the universe. Even more intriguing are ideas suggesting that higher dimensions could harbor alternate versions of our universe, existing in parallel. These parallel universes might interact with our three-dimensional space in subtle ways, influencing quantum phenomena and other mysterious events that have yet to be fully understood. The study of higher dimensions, while still largely theoretical, opens up vast new territories for scientific inquiry and exploration, offering the tantalizing possibility that our universe might be far stranger and more complex than we could have ever imagined. The concept of higher dimensions has fascinated physicists and cosmologists for many decades, offering a unique lens through which we can begin to understand the fundamental workings of the universe. Central to this exploration is string theory, a prominent framework within theoretical physics. String theory proposes that our universe may consist of up to 10 or even 11 dimensions, many of which remain imperceptible to our senses. These additional dimensions, hidden from view, might hold the key to explaining some of the most perplexing aspects of our physical reality, from the nature of gravity to the mysterious forces driving the expansion of the universe. One of the most intriguing ideas to emerge from the study of higher dimensions is their potential role in explaining the behavior of gravity. Gravity, as we experience it in our three-dimensional world, appears to be exceptionally weak compared to the other fundamental forces, such as electromagnetism and the strong nuclear force. This apparent weakness has baffled scientists for centuries. Some theories suggest that gravity might not be confined to our three-dimensional space, but could be leaking into additional dimensions. If this hypothesis is correct, it could provide an explanation for why gravity feels so weak in our universe, while other forces remain much stronger. This idea could also offer a path toward reconciling gravity with quantum mechanics, a long-standing challenge in physics that has eluded a unified theory. Beyond gravity, higher dimensions may also offer an explanation for two of the most mysterious phenomena in the cosmos: dark matter and dark energy. These enigmatic components appear to make up the entirety of the universe, yet we are unable to observe them directly. Some researchers have speculated that dark matter could be a manifestation of particles from higher dimensions interacting with our own. If particles from these unseen realms are interacting with our universe, they might be responsible for the gravitational effects attributed to dark matter. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, could also be influenced by higher dimensions. Perhaps the expansion of the universe is not just occurring in the three dimensions we observe, but also in additional dimensions that we cannot yet detect. Another mind-boggling phenomenon that might be linked to higher dimensions is quantum entanglement. This phenomenon describes a situation where two particles, no matter how far apart they are, can instantaneously affect each other. This appears to violate the principle that information cannot travel faster than the speed of light. Some theories suggest that entangled particles could be connected through higher dimensional space, providing a possible explanation for this seemingly impossible faster-than-light communication. If true, this would not only reshape our understanding of quantum mechanics, but could also offer a new perspective on the fabric of space-time itself. The implications of higher dimensions stretch far beyond gravity and quantum mechanics, extending to the large-scale structure of the universe. Higher dimensional space might alter the way matter behaves on a cosmic scale, leading to new insights into the distribution of galaxies and other cosmic structures. In our three-dimensional universe, matter tends to clump together under the influence of gravity. However, in a higher dimensional space, gravity could behave differently. It could spread out or disperse more rapidly than in our three-dimensional world, weakening the gravitational pull between distant objects. This could help explain the observation that galaxies appear to be moving apart faster than predicted by current models, a phenomenon known as cosmic acceleration. These additional dimensions might also provide a new perspective on the so-called voids in the universe, vast empty regions of space that seem to lack matter. Higher dimensions could allow for the existence of matter that is not directly observable in our three-dimensional world, leading to voids or concentrations of matter that remain hidden from view. Much like how a two-dimensional being would be unable to perceive the third dimension, we might be blind to structures and patterns that exist in higher dimensions. These invisible forces could be responsible for the strange effects we attribute to dark matter, suggesting that the universe is much more complex and interconnected than we currently understand. String theory, which posits that the fundamental building blocks of the universe are tiny, vibrating strings existing in multiple dimensions, may help explain how higher dimensions influence the distribution of matter in the cosmos. According to string theory, the way these strings vibrate and interact in higher dimensional space could have a profound impact on the organization of matter, potentially giving rise to the intricate web-like structure observed in the large-scale distribution of galaxies. If string theory is correct, the dynamics of these extra dimensions could be fundamental to the formation of the universe as we know it, guiding the distribution of galaxies, stars, and other cosmic entities. The role of higher dimensions in the expansion of the universe is another area of great interest. String theory suggests that the universe could have as many as 11 dimensions, with some of them compactified or curled up so tightly that they remain undetectable by our senses. Despite being hidden from view, these extra dimensions could still exert a significant influence on the universe's behavior. One fascinating possibility is that the expansion of the universe is being driven by the properties of these higher dimensions. As our three-dimensional universe expands, it might be interacting with or moving through these extra dimensions in ways that are beyond our current understanding. This interaction could explain the mysterious phenomenon of dark energy, which seems to be accelerating the rate at which the universe is expanding. String theory also introduces the concept of brains, multidimensional objects that exist in higher dimensional space. If our universe is a three-dimensional brain floating in a higher dimensional space, the movement or interaction of these brains could provide an explanation for the expansion of the universe, as well as offer a new perspective on cosmic inflation and the Big Bang itself. The idea that our universe is part of a larger, higher dimensional structure opens up exciting possibilities for understanding the origins and evolution of the cosmos. In addition to its impact on cosmic scale phenomena, higher dimensional space could have profound implications for the behavior of subatomic particles. In string theory, particles are not point-like objects, but rather tiny, vibrating strings that exist in 10 or 11 dimensions. Most of these dimensions are believed to be tightly curled up, making them undetectable in our everyday experience. However, their existence could help explain some of the perplexing behaviors observed in quantum mechanics. For example, higher dimensions might allow particles to shortcut through space-time, offering an explanation for quantum phenomena like entanglement, where particles instantaneously affect each other across vast distances. Additionally, the apparent weakness of gravity could be explained by the fact that gravity is spread across all dimensions, while the other fundamental forces are confined to our observable four-dimensional space-time. The presence of higher dimensions could also lead to the discovery of new particles or forces that we have not yet observed. If particles can interact across higher dimensional space, this could open up new avenues for scientific exploration, potentially leading to the discovery of new forms of matter and energy that have previously eluded detection. This could have far-reaching implications for our understanding of dark matter, dark energy, and the very nature of the universe. Higher dimensions also challenge our conventional understanding of time. In our familiar three-dimensional space, time flows in one direction, from past to present to future. However, if higher dimensions exist, time might not be restricted to this linear progression. Instead, it could be a multidimensional construct, allowing for multiple timelines or even the simultaneous existence of past, present, and future. This could potentially provide an explanation for phenomena like quantum entanglement, where particles appear to communicate instantaneously across vast distances, defying our traditional understanding of cause and effect. Higher dimensions could also allow for the existence of closed, time-like curves, paths through space-time that loop back on themselves, theoretically enabling time travel. While this idea remains speculative, it underscores the possibility that our perception of time may be limited by our inability to directly experience higher dimensions. As we continue to investigate these ideas, we may be forced to reevaluate our understanding of time and its role in shaping reality itself. The impact of higher dimensions on time could also have profound implications for the evolution of the universe. It might offer new insights into the nature of dark energy, the force that is driving the accelerated expansion of the cosmos, or provide alternative explanations for the arrow of time we observe. As we probe deeper into these concepts, it becomes increasingly clear that our current understanding of the universe is far from complete. Higher dimensions could hold the key to unlocking some of the most profound mysteries of existence, from the origins of the cosmos to the nature of time itself. The journey into higher dimensional space is just beginning, and the discoveries that lie ahead could fundamentally reshape our understanding of the universe. Higher dimensions, an abstract yet compelling concept, unlock an entire realm of possibilities for rethinking our understanding of the universe and the forces that govern it. Our universe, as we experience it, unfolds within a three-dimensional space intertwined with time, resulting in what we commonly perceive as four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. These forces shape everything we know, from the smallest particles to the grandest cosmic structures. Yet, the notion that there could be additional spatial dimensions beyond those we can directly observe introduces a revolutionary perspective on how these forces might behave, interact, and interconnect. The theory suggests that gravity, often viewed as the weakest of the fundamental forces, may not actually be weak at all. Rather, its apparent feebleness might arise because most of its strength is not confined to the familiar three dimensions we experience, but is instead leaking into higher, hidden dimensions. If this idea is correct, then gravity could be as powerful as the other fundamental forces, its subtle effect on our world simply a result of how its influence is spread thin across dimensions beyond our perception. If humans could access, manipulate, or even observe these extra dimensions, it could fundamentally alter how we approach physics, potentially unlocking technologies we have yet to imagine and offering new ways to harness the power of gravity. In addition to these tantalizing prospects, higher dimensions could offer a unified framework for understanding the fundamental forces that govern the universe. String theory, a leading candidate in the search for a theory of everything, proposes that our universe may contain as many as 10 or even 11 dimensions. In this framework, the extra dimensions are compacted to an incredibly small scale, too tiny for us to detect directly with current technology. String theory suggests that the forces we observe, gravity, electromagnetism, and the nuclear forces, might all be different manifestations of a single, unified force spread across the entire multidimensional fabric of the universe. These additional dimensions might also give rise to surprising, unexpected phenomena. For example, particles might be able to travel through higher dimensions, potentially bypassing the usual constraints of space and time. In our three-dimensional world, this could appear as if they are moving faster than the speed of light, challenging our understanding of causality, relativity, and the very structure of space-time itself. If these higher dimensions exist, they may even play a crucial role in the formation and evolution of galaxies, providing answers to mysteries about galactic behavior and cosmic structure that remain unsolved in current models. The distribution of dark matter, for example, which plays a key role in the formation of galaxies, could be influenced by the interactions between matter and the additional spatial dimensions. Dark matter is invisible to traditional detection methods, but it might be interacting with higher dimensions in ways that affect its clustering and distribution, offering clues to the peculiar behavior of galaxies and the unexpected rotational speeds of stars on their outskirts. Another fascinating implication of higher dimensions is their potential effect on galactic mergers and interactions. These cosmic collisions are fundamental to the evolution of galaxies, and if higher dimensions exist, they might influence how galaxies collide, merge, and form complex structures that we observe in interacting galaxies. This could offer new explanations for the unusual properties and behaviors of these systems, which have puzzled scientists for decades. In the search for evidence of higher dimensions, researchers are employing a variety of advanced methods and technologies. One approach involves studying particle collisions in facilities like the Large Hadron Collider, LHC, which accelerates particles to nearly the speed of light to create conditions similar to those that existed in the early moments of the universe. These high-energy collisions might produce anomalies, such as missing energy or unusual patterns in the resulting particles, that could be indicative of interactions with higher dimensions. Scientists are particularly interested in detecting microscopic black holes, which are predicted by some theories to form more easily in higher dimensional spaces. The appearance of these tiny black holes, followed by their rapid evaporation, could provide direct evidence for the existence of extra dimensions. Beyond particle accelerators, another promising avenue is the study of gravity itself. Gravity is theorized to potentially extend into additional dimensions, and scientists are conducting meticulous experiments at extremely small scales to measure gravitational forces and look for deviations from expected behavior. If the force of gravity behaves differently at these small scales, it could be a sign of higher dimensions at play. Gravitational wave detectors, which measure ripples in spacetime caused by massive cosmic events, could also offer important clues. These detectors might pick up anomalies in the waves they detect, signaling that gravitational waves are being altered by the existence of extra dimensions. Astronomers are also exploring the vast expanse of the universe to search for signs of higher dimensions. By studying phenomena such as the cosmic microwave background radiation, gravitational waves, and the large-scale structure of the universe, they hope to identify patterns or irregularities that might point to the presence of dimensions beyond our own. One key area of interest is the distribution of dark matter and dark energy, both of which make up the majority of the universe's content. If higher dimensions exist, they may provide a new framework for understanding how dark matter behaves and how it interacts with visible matter, potentially unlocking answers to some of the deepest questions in cosmology. The pursuit of evidence for higher dimensions also extends into the realm of quantum mechanics. Neutrinos, subatomic particles that are notoriously difficult to detect and pass through normal matter with ease, might offer another window into higher dimensions. The peculiar behavior of these particles could be explained by their ability to travel through additional spatial dimensions. This might also be true for gravitons, the hypothetical particles responsible for the force of gravity, which could move through extra dimensions in ways that affect how we perceive gravity in our three-dimensional space. String theory and its cousin, M theory, suggest that the true nature of our universe may involve up to 10 or 11 dimensions, with most of these dimensions being tightly compacted. The complexity of these theories has traditionally been too much for classical computers to handle, but quantum computers, with their ability to perform parallel computations and process vast amounts of information simultaneously, could offer a means to simulate higher dimensional spaces and unravel their secrets. Quantum computers could also help scientists explore the mathematical structures of string theory and M theory, offering insights into how these extra dimensions influence the behavior of particles, forces, and the fabric of space-time itself. Quantum computing may also be instrumental in simulating quantum gravity, a theory that seeks to reconcile the principles of quantum mechanics with general relativity. Quantum gravity often involves considering higher dimensional spaces, and quantum computers could provide the necessary computational power to model these complex and often counterintuitive scenarios. This could lead to new breakthroughs in understanding the relationship between space, time, and gravity, and how they might operate in higher dimensional frameworks. Gravitational wave detectors, too, present an exciting frontier in the search for higher dimensions. These sensitive instruments, which can detect the slightest ripples in the fabric of space-time, might be able to uncover subtle anomalies caused by the existence of extra dimensions. If the universe has additional dimensions, gravitational waves could behave in ways that are inconsistent with our current understanding of four-dimensional space-time. These waves might exhibit unexpected variations in strength, frequency, or direction, potentially revealing hidden aspects of the universe. Some theories even suggest that higher dimensional objects, such as black holes or other exotic cosmic phenomena, could create unique gravitational wave signals that stand out from the background noise, providing valuable evidence of a multidimensional reality. As astronomers look deeper into the cosmos, they are particularly interested in studying black holes, cosmic objects with gravitational fields so intense that not even light can escape their grasp. Black holes might hold the key to understanding the role of higher dimensions in shaping the structure of the universe. If extra dimensions exist, black holes could behave differently than we currently understand, potentially revealing new features that might provide vital clues to the hidden dimensions of space. The search for evidence of higher dimensions is a challenging and ambitious quest, one that requires pushing the boundaries of our technology and our understanding of physics. Yet as scientists continue to explore the universe on both microscopic and cosmic scales, the possibility of uncovering these hidden dimensions remains an exciting and transformative prospect that could fundamentally alter our view of reality itself. Some theories suggest that miniature black holes might serve as portals to hidden dimensions, offering a potential means for particles to escape the boundaries of our observable universe. These tiny, enigmatic objects, which are theorized to exist in places where gravity is intense enough to warp space-time, could act as gateways to realms beyond our perception, where the rules of physics as we know them may not apply. Cosmic inflation, the rapid expansion of the universe in its earliest moments, provides another intriguing pathway for investigating higher dimensions. According to certain models, this explosive growth was fueled by the separation of extra dimensions from our familiar four-dimensional space-time. If this hypothesis holds true, there may be subtle, lingering traces of this process imprinted in the cosmic microwave background radiation, the faint glow that permeates the universe, providing a potential clue to the existence of dimensions beyond the observable world. Dark matter and dark energy, the mysterious entities that make up the vast majority of the universe's mass and energy, might also be connected to higher dimensions. While we cannot directly observe these strange components, some scientists speculate that they could be manifestations of extraspatial dimensions, offering an explanation for their elusive nature and their unusual effects on visible matter and cosmic expansion. The existence of these invisible substances, while still theoretical, could help explain how galaxies and clusters of galaxies behave, as though they have far more mass than we can see. The unexplained acceleration of the universe's expansion might also be tied to the influence of these hidden dimensions, casting new light on the very structure of reality. Gravitational waves, the ripples that travel through the fabric of space-time, produced by cataclysmic cosmic events such as the collision of black holes or neutron stars, present yet another potential avenue for exploring the existence of higher dimensions. These waves, which carry information about the most violent and distant phenomena in the universe, could harbor clues to dimensions beyond the familiar four. If scientists develop more advanced detectors, they may one day spot anomalies in these waves that point to the influence of additional spatial dimensions, causing gravitational interactions to behave in ways our current understanding cannot predict. Such discoveries could transform our perception of the cosmos and open new frontiers in the study of the universe's fundamental nature. Neutrino detectors, tools capable of detecting the faintest, nearly invisible particles that travel through space, also hold great promise in the quest to understand the universe's hidden dimensions. Neutrinos, which interact so weakly with matter that they pass through entire planets without being affected, could provide valuable insights into realms beyond the three spatial dimensions we observe. One approach is to examine anomalies in neutrino oscillations. As neutrinos travel across the universe, they change from one type to another, a phenomenon known as neutrino oscillation. If extra dimensions exist, they might influence this oscillation in unexpected ways, causing deviations from the patterns predicted by current models. By precisely measuring these oscillations, scientists might detect the subtle imprint of hidden dimensions, opening up new possibilities for studying the very fabric of reality. Another potential clue lies in the energy and direction of neutrinos coming from distant cosmic sources. If extra dimensions are real, they could provide shortcuts through these hidden realms at allowing neutrinos to arrive at Earth faster than expected, or from directions that defy current models of space-time. Detecting such anomalies would not only provide indirect evidence for the existence of higher dimensions, but it could also revolutionize our understanding of how particles move through the universe. In addition, neutrino detectors might assist in the search for microscopic black holes, which some theories propose could be more easily created in particle accelerators if higher dimensions exist. These miniature black holes, short-lived and difficult to detect, could decay in ways that neutrino detectors might observe, offering tantalizing indirect evidence of the hidden dimensions that might lie just beyond our reach. Yet, proving the existence of higher dimensions is a formidable challenge for scientists. One of the primary obstacles is our limited sensory perception. Humans are able to directly observe and interact with only three spatial dimensions and one time dimension. This inherent limitation means that detecting or measuring any additional dimensions that might exist beyond our everyday experience is extraordinarily difficult. The mathematical models that describe these extra dimensions are often abstract and complex, requiring highly sophisticated tools to attempt to translate them into something observable. Furthermore, many theories suggest that these dimensions are either incredibly small, compactified, or hidden from our direct interactions, meaning they are essentially undetectable by our current technology. This makes any direct observation of extra dimensions nearly impossible with today's scientific instruments. The mathematical challenges involved in describing higher dimensions also present a significant hurdle. While theories can describe the structure of additional dimensions in elegant equations, translating these concepts into testable predictions or observable phenomena remains a daunting task. This gap between theoretical models and practical experiments makes it extremely difficult to conclusively prove the existence of higher dimensions, and it leaves room for skepticism in the scientific community. Additionally, the energy required to probe these hidden dimensions might exceed the capabilities of any existing particle accelerators or experimental setups. Some theories suggest that accessing or manipulating extra dimensions could require energies akin to those found in the early universe, energies far beyond what current technology can generate. This technological limitation adds another layer of difficulty to the quest for empirical evidence of higher dimensions. Despite these challenges, scientists remain committed to exploring the possibility of higher dimensions. They approach the search with a combination of rigorous mathematical frameworks, theoretical predictions, and ongoing efforts to find observable evidence. These theories arise from attempts to unify the fundamental forces of nature and to explain certain puzzling phenomena that current physics cannot fully address. For example, some models propose that gravity may behave differently at very small scales, potentially revealing subtle hints of extra dimensions. Others suggest that certain particle interactions could serve as a signature of higher dimensions, providing a testable prediction that scientists can attempt to confirm. Particle accelerators, precision measurements of gravity, and astronomical observations are all being utilized to search for these effects, and researchers continue to refine their methods in the hope of uncovering something new. The explanatory power of higher dimensional theories is another driving force behind their pursuit. These models could offer solutions to long-standing puzzles in physics, such as the hierarchy problem, which seeks to explain why gravity is so much weaker than the other fundamental forces, or the nature of dark matter and dark energy, which remain elusive despite comprising most of the universe's mass and energy. By demonstrating how extra dimensions could solve multiple mysteries at once, scientists build a compelling case for the plausibility of these ideas. They emphasize that these theories are not simply speculative, but are grounded in mathematical consistency and in some cases are linked to established physical principles. Moreover, scientists are open to engaging with skeptics, addressing critiques, and refining theories based on feedback. They acknowledge the speculative nature of these ideas while reinforcing their mathematical soundness and their potential to address significant gaps in our understanding of the universe. This process of transparency and constant refinement helps maintain scientific integrity, ensuring that the search for higher dimensions remains grounded in reason and evidence. Though the models we have are far from perfect, they represent our best efforts to understand a universe that continues to challenge our deepest assumptions. Our current mathematical models, though powerful, have significant limitations when it comes to fully describing higher dimensions. These models allow us to conceptualize extra dimensions, but they remain theoretical, unable to be directly tested by experimentation. As such, they cannot be easily verified or falsified, which makes the search for experimental evidence all the more crucial. Predictions made by these models may guide future research, but as we venture beyond the fourth dimension, confirming the accuracy of these models becomes increasingly difficult. Nonetheless, the pursuit of higher dimensions continues, driven by the hope that we might one day unlock the hidden structure of the universe and reveal the secrets of the cosmos that remain just beyond our grasp. The human brain, shaped by millions of years of evolution, is finely tuned to navigate a three-dimensional world. Yet this same brain struggles to comprehend the intricate nature of higher dimensional spaces. Our evolutionary path, grounded in the physical reality of three spatial dimensions and one dimension of time, limits our capacity to visualize and intuitively understand any additional spatial dimensions that may exist. This constraint is not just a matter of curiosity. It presents a profound challenge for scientific inquiry. Mathematical models and theoretical frameworks are essential tools that allow us to probe beyond these limitations, offering abstract representations of higher dimensional spaces. However, these models, though intellectually powerful, cannot bypass the fundamental hurdle of human perception, which remains rooted in a three-dimensional worldview. As scientists delve into the complexities of higher dimensional systems, they confront an escalating challenge in the form of computational complexity. When attempting to model these systems, the number of variables and interactions increases exponentially with each additional dimension, quickly overwhelming even the most advanced computers. The limits of our computational power create practical barriers to fully exploring or simulating the behavior of higher dimensional systems, no matter how sophisticated our algorithms may become. The quest to extend our understanding of the universe to dimensions beyond the familiar three is thus constrained by both our cognitive abilities and our technological limitations. At the forefront of this search for deeper understanding lie theories, such as string theory, which propose the existence of additional spatial dimensions beyond the three we directly experience. These theories aim to provide explanations for a variety of physical phenomena that cannot be fully accounted for within the confines of classical physics. However, these ideas are not without their own set of difficulties. The lack of direct observational evidence for the existence of extra dimensions presents a significant challenge. These higher dimensions are theorized to be so minuscule that they are curled up or compactified to scales smaller than the smallest distances measurable by current technology. Even with the most cutting-edge instruments available, we are unable to detect these extra dimensions directly. Instead, they remain an abstract possibility, supported by elegant mathematical models, but lacking the concrete proof that would elevate them to the status of empirical science. This lack of direct evidence has sparked fierce debates within the scientific community. Critics argue that without tangible proof, higher dimensional theories remain speculative and cannot be considered scientifically valid. On the other hand, proponents of these theories emphasize their mathematical consistency and explanatory power, insisting that these abstract concepts are worth exploring further. Despite the absence of direct proof, scientists continue to develop indirect methods to test the validity of higher dimensional theories. One of these methods involves searching for specific particle interactions in particle accelerators, which could reveal subtle signs of extra dimensions. Another approach involves measuring gravitational effects at very small scales or analyzing cosmic radiation for any indications of extra-dimensional influences. While these efforts have yet to yield conclusive evidence, they serve as a testament to the persistence and ingenuity of the scientific community in the pursuit of knowledge. The exploration of higher dimensional spaces is not simply a matter of abstract speculation. It is profoundly influenced by the limitations of our three-dimensional existence. The human brain, which evolved to process and interpret sensory data from the three dimensions of space, finds it nearly impossible to conceptualize dimensions beyond length, width, and height. This inherent limitation in our cognitive abilities means that even the most advanced mathematical models and theoretical constructs struggle to provide an intuitive understanding of higher dimensional spaces. Our sensory systems, too, are ill-equipped to perceive phenomena that lie outside the bounds of the three dimensions we encounter daily. Instruments and sensors, which are designed to measure and interact with the physical world as we know it, are constrained by the same fundamental limitations, making it exceedingly difficult to directly probe or manipulate higher dimensional spaces. Moreover, our technology, although advancing rapidly, is still grounded in the principles of classical physics, which operate within the three-dimensional universe we can observe. As we attempt to extend our technological reach into higher dimensional realms, we encounter significant hurdles. The enormous energies that might be required to influence or access higher dimensional phenomena are far beyond our current capabilities. Even with the most powerful supercomputers, the task of simulating and analyzing higher dimensional systems remains a daunting challenge. The computational power required to model these systems increases exponentially with each additional dimension, making it almost impossible to fully understand or predict the behavior of these higher dimensional spaces using current technology. Yet, despite these challenges, researchers continue to explore ways to reconcile the concept of higher dimensions with the established laws of physics. One of the most important strategies involves the idea of compactification, which suggests that while additional dimensions may exist, they are so minuscule that they are curled up or compacted to scales far beyond our ability to detect. These compact dimensions, theorized to be as small as the Planck length, the smallest measurable distance in physics, would have no observable effects at larger scales, allowing our three-dimensional world to appear as it does. Another method used by physicists is dimensional reduction, a mathematical technique that allows the description of higher dimensional theories in terms of lower dimensional models. By carefully reducing the number of dimensions in a model, scientists can preserve the key features of the higher dimensional theory while ensuring that predictions align with the physical laws we observe in our everyday reality. As experimental physicists continue to push the boundaries of knowledge, they test the predictions of these higher dimensional theories in a variety of ways. They look for minute deviations in the behavior of fundamental forces, such as gravitational anomalies at very small distances, or the creation of microscopic black holes in particle accelerators. While these experiments have not yet produced definitive evidence for the existence of extra dimensions, they continue to refine our understanding of the universe and may one day provide the breakthrough needed to confirm or refute these theories. The pursuit of higher dimensional theories requires significant funding and resources to support the infrastructure needed for cutting-edge research. Large-scale particle accelerators, like the Large Hadron Collider, LHC at CERN, which costs billions of dollars to construct and maintain, play a crucial role in providing the experimental conditions necessary to explore fundamental questions about the universe. Financial support also enables theoretical physicists to develop complex mathematical models and hypotheses, which in turn guide experimental design and interpretation. In addition, funding fosters collaboration across disciplines, bringing together experts from various fields to tackle the many challenges inherent in studying higher dimensions. This collective effort, facilitated by adequate financial resources, accelerates scientific progress and increases the chances of revolutionary discoveries that could reshape our understanding of the cosmos. In the delicate balancing act between theoretical exploration and scientific rigor, physicists must tread carefully. Theoretical concepts often venture into realms far beyond the reach of current technology, challenging our existing understanding of the universe. To maintain scientific credibility, these ideas are subjected to rigorous peer review and mathematical scrutiny. Researchers are careful to distinguish between well-supported theories and more speculative ideas, using phrases like, according to our current understanding, or this model suggests, to clarify the level of certainty surrounding their hypotheses. The scientific community plays an essential role in this process, critically examining new theories and demanding empirical evidence before accepting them. This collective effort ensures that the pursuit of knowledge remains grounded in the scientific method, guiding theoretical physics toward productive investigations of the universe's most profound mysteries. Understanding higher dimensions could fundamentally transform the landscape of human technology, opening doors to innovations that today feel like the realm of science fiction. By exploring and grasping the nature of dimensions beyond the familiar three of space and one of time, researchers, engineers, and inventors might uncover new principles that redefine how we generate power, move through space, communicate, and process information. In energy generation, higher dimensional physics presents the tantalizing prospect of tapping previously inaccessible forces. Theoretical models suggest that gravity could behave differently in higher dimensions, potentially amplifying its effects. If humanity could harness these forces, it might lead to energy systems far more efficient and potent than anything currently imaginable, allowing societies to power entire cities or even entire nations with minimal environmental impact. Transportation could undergo equally dramatic evolution. The ability to manipulate extra spatial dimensions might make it possible to create shortcuts through the fabric of space and time, essentially compressing vast distances into manageable scales. This could translate into faster-than-light travel, near instantaneous transportation between distant planets, or revolutionary methods of moving people and goods across the globe. The implications for space exploration are staggering. What now takes decades or centuries to reach might become a matter of weeks or even days, fundamentally reshaping humanity's relationship with the cosmos. Computing and information processing, too, could see profound changes through higher dimensional applications. Quantum computers, for instance, rely on the manipulation of quantum bits, or qubits, which exist in multiple states at once. Higher dimensional insights could expand these capabilities, allowing computers to solve problems that are currently intractable, from cracking complex encryption to modeling global climate systems with unprecedented precision. By exploiting particles that interact across multiple dimensions, scientists could design algorithms capable of navigating complexity in ways classical computing cannot match, accelerating discoveries in medicine, engineering, and artificial intelligence. The implications for space exploration extend beyond speed. Higher dimensional theories suggest that what appear as vast distances in our three-dimensional perception might actually be shortcuts accessible through additional dimensions. These wormholes could allow travel between distant points in the universe almost instantaneously. Beyond navigation, these hidden dimensions might also account for some of the universe's most enigmatic phenomena, such as dark matter and dark energy. Understanding these forces could illuminate the structure and evolution of the cosmos itself, guiding future exploration and even offering clues about the universe's ultimate fate. Propulsion technology, too, could be revolutionized. Harnessing forces or energy from higher dimensions could allow spacecraft to travel with extraordinary efficiency, overcoming the immense energy demands of interstellar voyages. Such breakthroughs could make previously unreachable star systems accessible, reshaping the very concept of space exploration. In computer science and artificial intelligence, higher dimensional frameworks play a pivotal role. High-dimensional data spaces allow machine learning algorithms to recognize intricate patterns and relationships invisible in lower-dimensional analysis. Techniques like principal component analysis reduce complexity, extracting essential information from massive data sets, which is critical for genomics, climate modeling, and social network analysis. In quantum computing, the superposition of qubits and higher dimensional geometries enable calculations at speeds that dwarf conventional computing. Incorporating topological and manifold concepts into neural networks could produce AI models that are more flexible, efficient, and capable of solving problems in natural language processing, computer vision, and autonomous systems at unprecedented levels. Medicine, too, could be transformed. Higher dimensional imaging could allow doctors to observe the human body from entirely new perspectives, uncovering hidden structures or abnormalities that are invisible in traditional three-dimensional scans. In pharmacology, understanding proteins and molecular interactions in higher dimensions could lead to highly targeted drugs with enhanced effectiveness. Surgical procedures might become extraordinarily precise, with tools manipulated through extraspatial dimensions to minimize tissue damage and recovery time. Genetic research could also benefit, as higher dimensional models provide deeper insight into the complex folding and organization of DNA, enabling more advanced gene editing technologies and new treatments for hereditary conditions. Energy production and storage could see innovations that defy conventional imagination. Accessing energy within extra dimensions might offer near-limitless clean power, far surpassing current energy sources. Compact energy storage devices exploiting these hidden dimensions could hold immense power in tiny physical footprints, revolutionizing everything from electric vehicles to renewable energy grids. Likewise, energy transfer could be transformed at allowing near-lossless distribution across vast distances, possibly even enabling instantaneous power delivery across continents. While much of this remains theoretical, these concepts illustrate a vision of the future in which higher dimensional understanding reshapes our technological, scientific, and societal capabilities, transforming the very way humanity interacts with the world and the universe around it. Higher dimensional understanding has the potential to utterly transform telecommunications in ways that stretch the imagination beyond our current grasp. Our present-day communication networks, built to function within the confines of three spatial dimensions plus the relentless march of time, are already marvels of engineering. Yet they remain fundamentally limited by the dimensions we perceive and interact with daily. Imagine, however, if we could access the hidden properties of higher dimensions, tapping into realms beyond our sensory experience. The implications for transmitting information are staggering. Consider quantum entanglement, a phenomenon where particles separated by vast distances behave as if connected instantaneously. In higher dimensions, entanglement could operate on an entirely new scale, allowing messages to traverse space without delay, collapsing the constraints of conventional signal speed. Global communication could become nearly instantaneous, removing latency as a barrier and vastly accelerating the flow of information across continents and oceans. Beyond mere speed, higher dimensions offer revolutionary avenues for encoding and compressing data. Just as three-dimensional objects cast intricate two-dimensional shadows, information from higher dimensions could be projected into our familiar three-dimensional space in ways that multiply storage and transmission capacity exponentially. Data might flow not linearly, but across layers and folds of space, condensed and expanded with a complexity previously unimaginable. Imagine communication networks where interference from physical barriers, electromagnetic noise, or even natural obstacles no longer exist. Signals could navigate extra-dimensional routes, circumventing obstructions entirely, resulting in unprecedented reliability and security. Industries from mobile telecommunications to deep space satellite networks would be fundamentally transformed, unlocking efficiencies that redefine the very concept of connectivity. Transportation, too, could be utterly reconceived. If higher dimensional pathways could be accessed, movement might no longer be constrained to forward, backward, left, or right. Vehicles could traverse routes that slice through the fabric of space itself, dramatically shortening travel times. Wormholes, theoretical tunnels through space-time connecting distant points in the universe, could shift from speculative physics to practical reality if we learn to stabilize and manipulate higher dimensional structures. Earthbound travel could become instantaneous across continents, and interstellar exploration might shift from dream to achievable mission. On a local scale, additional dimensions could dissolve the traffic congestion that paralyzes modern cities. Vehicles navigating multiple spatial layers would unlock infinite routing possibilities, reshaping urban planning, infrastructure design, and daily commuting, turning once crowded thoroughfares into fluid conduits of movement. Yet the challenges are formidable. Engineering vehicles and infrastructure capable of interacting with higher dimensions requires technological leaps that border on the fantastical. We remain in the early stages of understanding, yet the allure of these possibilities drives scientists and engineers to push boundaries relentlessly. Cryptography, too, could undergo a revolution. Higher dimensional mathematics could produce encryption systems far more intricate and secure than those available today. By leveraging extra-dimensional geometry, information could be encoded in ways classical computing cannot breach. Quantum cryptography, already a frontier of security, might benefit further, with higher dimensions enabling new key distribution systems and post-quantum cryptographic algorithms designed to withstand the advent of powerful quantum computers. Steganography, the art of hiding information, could see dramatic evolution, concealing greater volumes of data across dimensions inaccessible to conventional observation. The quest to understand higher dimensions pushes the boundaries of physics itself. Researchers are probing the possible existence of extra dimensions that could explain dark matter or unify gravity with other fundamental forces. The holographic principle suggests our three-dimensional universe may be a projection from a two-dimensional surface, challenging perceptions of reality and space-time. String theory posits tiny vibrating strings as the universe's fundamental building blocks, each existing in multiple dimensions. Detecting these extra dimensions could revolutionize cosmology and our understanding of existence. Quantum gravity remains an essential frontier, as higher dimensional models might reconcile quantum mechanics with general relativity, illuminating black holes, the Big Bang, and the ultimate fate of the cosmos. Quantum computing offers unparalleled tools for these explorations. These machines process information in ways classical computers cannot, simulating systems with massive complexity and numerous variables. Problems once thought computationally insurmountable due to exponential scaling become tractable under quantum computation. Researchers can explore string theory's extra dimensions, simulate quantum gravity scenarios, and analyze astronomical or particle physics data for subtle anomalies indicating higher dimensions. This could finally bring empirical evidence to theories that until now have resided solely in abstract mathematics. Artificial intelligence and machine learning amplify these capabilities. AI can sift through vast data sets from particle accelerators, cosmic observations, and experimental results, identifying subtle patterns imperceptible to humans. It can simulate and visualize higher dimensional spaces, making abstract models tangible. AI can even propose new mathematical frameworks for understanding extra-dimensional phenomena, offering innovative pathways to unify quantum mechanics and general relativity. Space missions expand this frontier further. Deep space observations, advanced telescopes, and gravitational wave detection provide new insights into the nature of space-time and extra dimensions. Interplanetary and interstellar travel tests our physical theories under extreme conditions, probing relativity, gravity, and the potential existence of hidden dimensions. Quantum experiments in space might clarify the interaction between quantum mechanics and gravity, bringing us closer to a unified physical theory. Mathematicians and physicists are relentless in exploring these possibilities, particularly through string theory, which suggests our universe may comprise up to 11 dimensions. Developing new mathematical tools and frameworks is essential to navigate this complexity. Each step in this pursuit, from theory to simulation to experimental validation, draws humanity closer to unlocking the full potential of higher dimensional understanding, reshaping telecommunications, transportation, cryptography, and our grasp of reality itself, while expanding the horizons of what the universe truly is. Calabi-Yau manifolds are central to modern theoretical physics, representing intricate six-dimensional geometric structures that may account for the hidden extra dimensions predicted by string theory. These shapes are not merely abstract mathematical curiosities. They are thought to hold the key to understanding the underlying architecture of the universe. Mathematicians are tirelessly developing new methods to classify and decode the properties of these manifolds, seeking patterns and symmetries that could illuminate the fundamental laws governing reality. Each breakthrough in understanding these structures opens doors to potentially revolutionary insights about the universe's composition, the behavior of matter, and the forces that bind it all together. And another paradigm pushing the boundaries of theoretical physics is twistor theory, initially introduced by Roger Penrose. This framework transforms points in space-time into geometric objects embedded in a higher dimensional context, offering a radically different way to approach the reconciliation of quantum mechanics with general relativity. Recent advancements in twistor theory are reshaping perspectives on particle physics, providing innovative tools for modeling interactions and unifying forces. Researchers are also investigating emergent dimensions, a concept where higher dimensional structures materialize from more fundamental, lower dimensional systems. Developing mathematical models for these emergent phenomena might explain how the familiar four-dimensional space-time we inhabit arises from a deeper, more elemental substrate, challenging our intuitive notions of reality. Exploring higher dimensions carries profound implications not only for physics, but also for our understanding of consciousness. Philosophers and scientists have long debated the nature of awareness, and higher dimensional frameworks may offer unprecedented insights. It is conceivable that consciousness itself is a higher dimensional phenomenon. Much as a two-dimensional being would struggle to perceive a three-dimensional world, our three-dimensional cognition may be fundamentally limited in grasping the full essence of awareness. These higher dimensional models could potentially unravel mysteries of consciousness that currently elude explanation. Some theories suggest that the human brain might act as a receiver, attuning to consciousness that exists in dimensions beyond our perception. This hypothesis aligns with certain interpretations of quantum mechanics, implying that the enigmatic behaviors observed in the quantum realm may be manifestations of interactions with higher dimensional structures. If consciousness emerges from or interacts with quantum processes, then higher dimensional models could provide a framework for comprehending the origins and mechanics of awareness. Investigations into higher dimensions could also shed light on altered states of consciousness, near-death experiences, and other phenomena that challenge conventional scientific frameworks. By extending the conceptual toolbox of physics and philosophy, researchers may develop new methodologies for understanding experiences that straddle the boundary between subjective perception and objective reality. Current research into higher dimensional theory is actively expanding the frontiers of cosmology and fundamental physics. Scientists are probing the existence of additional spatial dimensions beyond the three familiar ones. If these dimensions exist, they could resolve some of the most perplexing mysteries of modern physics. One major area of investigation involves high-energy particle collider experiments, where researchers hope that colliding particles at unprecedented energies might reveal evidence of interactions with hidden dimensions. Detecting particles or forces leaking into or emerging from these dimensions would fundamentally transform our comprehension of reality. Mathematical models incorporating higher dimensions are being refined, offering potential paths toward unifying quantum mechanics with general relativity, two pillars of physics that have long resisted synthesis. A successful unification would yield a comprehensive framework describing the universe at all scales, from the subatomic to the cosmological. Advancements in gravitational wave astronomy may also reveal signatures of higher dimensional influences. As detection and analysis of gravitational waves become increasingly precise, Scientists anticipate the possibility of observing gravitational effects originating from dimensions beyond the observable universe, unlocking new methods for testing theories of space, time, and matter. Higher dimensional research has profound implications for understanding the universe's origin. Cosmologists are considering whether our universe is embedded in a larger multidimensional structure, a scenario that could illuminate enigmatic aspects of cosmic formation. One fascinating model posits that our universe is a three-dimensional brain floating in higher dimensional space. In this framework, the Big Bang may not represent the absolute beginning, but could result from collisions between such brains, potentially explaining the rapid inflationary expansion observed in the early universe and offering insights into the nature of dark energy and dark matter. String theory further enriches this perspective by suggesting that the universe contains 10 or 11 dimensions, with fundamental constituents manifesting as tiny vibrating strings. The interactions of these strings across multiple dimensions could give rise to the universe's physical laws and the apparent fine-tuning of constants that govern its behavior. Higher dimensional models may also help solve the long-standing puzzle of quantum gravity, merging the physics of the very small with the physics of the very large, and shedding light on the earliest moments of existence when space, time, and matter emerged from a primordial state. Biologists are entering this frontier by investigating higher dimensions in living systems, bridging biology with theoretical physics. Protein folding, a fundamental process determining the shape and function of biological molecules, is being examined through higher dimensional models to reveal hidden structural patterns inaccessible in 3 dimensions. Similarly, the intricate networks of neurons in the brain may be more accurately represented in higher dimensional spaces, offering transformative insights into cognition, memory, and consciousness. Evolutionary biology is also exploring higher dimensional frameworks to understand diversification and the emergence of life, seeking new explanations for patterns of biodiversity and evolutionary dynamics that remain elusive in conventional three-dimensional analyses. In modern cosmology, higher dimensions extend our understanding far beyond the familiar 3 spatial dimensions and 1 temporal dimension. Theories such as string theory posit that additional dimensions are not theoretical curiosities, but essential components of a deeper, unified understanding of the cosmos. As research progresses, these higher dimensional models promise to reshape the boundaries of physics, biology, and philosophy, potentially transforming our grasp of the universe, consciousness, and the fundamental principles that underlie existence itself. Most of these additional dimensions are believed to be tightly curled up, unimaginably small, existing at scales far beyond the reach of conventional measurement, far smaller than even a single atom. They are hidden layers of reality, imperceptible to our senses, yet potentially holding the answers to some of the deepest mysteries in physics. For example, they might explain why gravity appears so weak compared to the other fundamental forces, as it could be diffusing into these hidden dimensions, diluting its effect in the world we experience. These higher dimensions also open the door to the tantalizing concept of parallel universes, suggesting that our observable cosmos could be only one of countless others, all existing within a vast, multidimensional expanse. In cosmology, these extra dimensions offer potential solutions to the enigmas of dark matter and dark energy. Theorists propose that dark matter particles might traverse these hidden realms, accounting for their ghostly, nearly imperceptible interactions with ordinary matter. Similarly, the accelerating expansion of the universe attributed to dark energy might arise from gravity behaving differently when influenced by dimensions beyond our three-dimensional perception. While these models remain largely theoretical and experimentally elusive, they continually inspire research, challenging scientists to rethink the very foundations of the cosmos. As observational technologies advance and new methods emerge, researchers hope to uncover evidence that could confirm or disprove these higher dimensional theories, potentially transforming our understanding of the universe at its most fundamental level. In chemistry, the concept of higher dimensions is reshaping our understanding of molecules and their behaviors. Traditional three-dimensional models, while useful, often fail to capture the full complexity of molecular interactions. By incorporating higher dimensional frameworks, chemists can represent molecular dynamics with far greater accuracy. One key application lies in mapping the potential energy surfaces of molecules, which chart every possible configuration a molecule can adopt and the energy associated with each state. Although these surfaces are often visualized in 3 dimensions, the true landscape is vastly more complex, often requiring dozens or hundreds of dimensions to fully describe the degrees of freedom in a system. This approach is particularly transformative in the study of protein folding, a process central to biology and medicine. The folding landscape of a protein is extraordinarily intricate, with countless possible conformations. Higher dimensional models allow researchers to predict folding pathways and interactions with unprecedented precision, paving the way for breakthroughs in drug design, treatment of diseases, and understanding of fundamental biological processes. Furthermore, quantum chemistry benefits immensely from these multidimensional frameworks. Quantum systems involve numerous interacting particles, each with unique variables, and higher dimensional mathematics enables accurate modeling of these complex interactions, enhancing predictions of molecular properties and reactivity. This advanced modeling underpins innovations in catalysts, material science, and nanotechnology, offering tools to manipulate matter at the smallest scales with extraordinary precision. In computer graphics and animation, higher dimensional theories are revolutionizing how we represent and manipulate visual information. These concepts allow programmers and artists to construct increasingly complex and realistic digital environments. In geometric modeling, for instance, higher dimensional mathematics enables the creation of intricate, flexible structures, facilitating smooth transitions between shapes and forms that appear lifelike. It allows the representation of objects that would be impossible to render in conventional 3-dimensional space. In lighting and rendering, higher dimensional perspectives on light interactions empower engineers to develop algorithms that simulate shadows, reflections, and material properties with extraordinary realism, enriching the depth and authenticity of virtual worlds. Motion planning and character animation similarly benefit, as representing movements in higher dimensional spaces enables fluid, nuanced motions, allowing digital characters to interact convincingly with their surroundings and with each other. Economists are also increasingly embracing higher dimensional models to navigate the complexity of modern markets. These sophisticated tools allow the simultaneous analysis of countless variables, offering a nuanced understanding of economic systems far beyond the capabilities of traditional models. With computational power, economists can integrate vast datasets, capturing factors such as consumer behavior, global events, and psychological influences, all within a single multidimensional framework. These models uncover hidden patterns, predict market shifts, and identify risks or opportunities that simpler analyses might miss. They also enable scenario simulations, allowing policymakers to test interventions virtually and anticipate outcomes before implementing decisions, ultimately guiding more informed and effective economic strategies. Higher dimensions are extending into the study of human consciousness, providing frameworks to explore the profound complexity of awareness. By conceiving thought, perception, and cognition within multidimensional spaces, researchers are beginning to approach questions about the nature of consciousness from angles previously inaccessible. These approaches suggest that human awareness may not be confined to the apparent 3 dimensions, opening the possibility that our minds interact with a reality far richer and more intricate than everyday experience reveals. In every field, from physics to chemistry, from computational design to economics, and even the exploration of consciousness, the concept of higher dimensions is more than a theoretical curiosity. It is a dynamic, transformative lens through which humanity is discovering new structures, behaviors, and connections, pushing the boundaries of understanding and inviting us to imagine a universe far more complex and wondrous than we ever perceived. Researchers investigating the nature of consciousness through the prism of higher dimensions draw heavily from advanced theoretical physics and abstract mathematics, particularly the intricate frameworks of string theory and M-theory. These groundbreaking theories propose that our universe may not be confined to the 4 dimensions we experience daily, 3 dimensions of space and 1 of time, but could instead encompass 10, 11, or potentially even more dimensions. Within the field of consciousness studies, these additional dimensions are considered as possible arenas in which the phenomenon of consciousness might operate, emerge, or even originate. One of the more compelling hypotheses suggests that consciousness itself could be a higher dimensional entity projecting into the 4-dimensional reality we inhabit. This idea resonates with certain philosophical perspectives, particularly the notion that what we perceive as conscious experience might be akin to shadows or projections cast by a more fundamental, higher dimensional reality. Advocates argue that this conceptual framework could shed light on the elusive, non-physical qualities of consciousness, as well as its apparent detachment from the physical brain. Skeptics caution, however, that while these higher dimensional models of consciousness are intellectually stimulating, they remain largely speculative and extraordinarily difficult to test empirically. Yet, the exploration of consciousness through this higher dimensional lens continues to inspire innovative approaches to one of humanity's oldest and most profound questions: how subjective experience arises from the material universe. In the realm of geology, scientists are employing higher dimensional mathematics to deepen their understanding of Earth's complex, interconnected systems. This avant-garde approach allows researchers to analyze and model intricate relationships between geological processes that had previously eluded comprehension through conventional methods. One critical area where higher dimensional thinking is proving transformative is in the study of plate tectonics. By conceptualizing Earth's crust as a multidimensional surface, geologists can construct more accurate models of how tectonic plates interact, encompassing subduction zones, transform faults, and mid-ocean ridges. This elevated perspective enables improved predictions of earthquake activity and volcanic eruptions, providing insights that could enhance disaster preparedness. Climate science, too, is reaping the benefits of higher dimensional analysis. Researchers are using these mathematical frameworks to trace the complex interplay between atmospheric phenomena, ocean currents, and terrestrial processes. By representing these systems in multiple dimensions, scientists can build more sophisticated climate models capable of accounting for the intricate feedback loops that drive Earth's climate. Additionally, these higher dimensional methods are enhancing our understanding of Earth's internal structure. By applying multidimensional mathematics to seismic data, geologists can produce detailed maps of the planet's core, mantle, and crust, revealing previously hidden dynamics of internal heat distribution and its influence on surface geology. Higher dimensional theories have also made a profound impact on the field of information theory, transforming our understanding of how data can be structured, transmitted, and protected. These theories propose that information may exist not only in the 3 spatial dimensions and time, but also within additional dimensions beyond ordinary perception. This insight has been particularly revolutionary in quantum information theory, where higher dimensional considerations have facilitated the creation of new models for quantum communication and computation. Such models allow for more complex entanglement states and open possibilities for more efficient processing and transmission of quantum information. In error correction, the introduction of higher dimensional frameworks has led to more robust coding systems, enabling data to be safeguarded against noise and interference, ensuring more reliable communication networks. Moreover, these approaches have revolutionized data compression techniques, allowing information to be mapped across higher dimensional spaces, which can result in unprecedented efficiency in storage and transmission in today's data-driven world. The notion of higher dimensional control carries profound implications for human behavior, decision-making, and the concept of free will. If our reality is shaped or influenced by dimensions beyond our perception, it could fundamentally alter our understanding of personal agency and responsibility. Individuals might begin to approach problem-solving and long-term planning differently, aware that unseen factors could be influencing outcomes. This awareness could encourage openness to unconventional solutions and the exploration of seemingly unrelated pathways when confronted with complex challenges, fostering innovation and creativity across multiple domains. On a societal scale, the concept of higher dimensional influence could reshape legal and ethical frameworks. Questions of accountability, intent, and responsibility might need to be reconsidered if human actions are potentially guided by forces outside our conventional three-dimensional understanding. This reevaluation could have sweeping consequences for justice systems, affecting how societies conceptualize rehabilitation, culpability, and social norms. Philosophically and spiritually, it could bridge the divide between science and mysticism, promoting a holistic worldview in which individuals perceive themselves as integral components of a larger, interconnected cosmic system. Such a perspective could nurture empathy, environmental stewardship, and a heightened sense of universal responsibility. In the legal arena, higher dimensional influence could challenge foundational notions of causality, free will, and personal responsibility. If our universe is governed by higher dimensional forces, human decisions and actions may be partially predetermined or influenced by factors beyond observable reality. This possibility could transform criminal law, where the concept of intent is critical, potentially undermining assumptions about culpability. Defense attorneys might argue that their clients' actions were compelled by forces beyond conscious choice. Civil law could also be affected, especially regarding contracts, torts, and the principles of informed consent. Traditional notions of negligence may require reconsideration if behavior is partially determined by higher dimensional influences. However, these considerations remain speculative, requiring substantial empirical support before influencing legal practice, with contemporary systems continuing to operate on the assumption of individual agency within observable reality. In politics, the idea of higher dimensional control could redefine power, governance, and perceptions of reality itself. The possibility that our three-dimensional universe is influenced or controlled by entities or forces from higher dimensions invites a radical rethinking of political structures and ideologies. Such a shift could inspire new frameworks for understanding leadership, policy, and social organization, challenging deeply ingrained assumptions about the nature of authority and societal order. Exploring these concepts illuminates the vast, largely uncharted territory where physics, consciousness, geology, information theory, ethics, law, and politics intersect, offering a vision of reality that is simultaneously intricate, profound, and deeply transformative. Some might argue that the political systems we rely on today are fundamentally inadequate to navigate the staggering complexities of a reality that stretches far beyond our conventional understanding. In a world where multidimensional forces might be at play, the familiar structures of governance could prove insufficient, giving rise to entirely new forms of political organization that attempt to account for influences from higher dimensions. This could dramatically reshape how we view both individual and collective agency within these systems. If higher dimensional entities exert significant control over the fabric of reality, the very notion of human autonomy and decision-making could be challenged, leading to profound questions about freedom, responsibility, and the legitimacy of our political institutions. Yet, the presence of such forces might not only induce a sense of powerlessness, it could equally inspire innovative efforts to comprehend, engage with, and even harness these higher dimensional influences for the greater good of society. The potential existence of higher dimensional control has the capacity to blur the traditionally distinct boundaries between science, politics, and spirituality, forging new ideological frameworks that integrate these domains in unprecedented ways. Political movements might emerge with the explicit aim of aligning human governance with perceived higher dimensional laws or principles, seeking to synchronize earthly affairs with the grand architecture of a universe that operates on levels beyond ordinary perception. Belief in such forces would inevitably carry profound psychological consequences, influencing both individual worldviews and the collective consciousness of entire societies. The idea that beings or energies from dimensions beyond our observable reality could subtly steer or manipulate our world might foster a sense of cosmic insignificance, leaving people to question the efficacy and meaning of their choices. For some, this could lead to fatalism or resignation, rationalizing personal setbacks, social crises, or global catastrophes as the inevitable outcome of higher dimensional interference. Conversely, many might find solace in the notion of a structured cosmos governed by intelligible higher forces. This perspective could transform chaotic or inexplicable events into manifestations of a greater order, imparting meaning and coherence to experiences that otherwise seem random. It might also ignite a deep curiosity, driving people to explore fringe sciences, metaphysical theories, and spiritual practices in search of a connection to these elusive dimensions. In extreme instances, the pursuit of patterns and hidden truths could veer toward paranoia or conspiratorial thinking, as individuals attempt to discern the subtle fingerprints of higher dimensional influence in everyday life. Ultimately, the psychological effects of such beliefs would vary widely, shaped by personality, cultural context, and the particular nature of the belief system itself, ranging from existential anxiety to a profound sense of cosmic unity. The exploration of higher dimensions could also transform educational systems, fundamentally expanding our conception of reality and challenging conventional ways of thinking. As we move beyond the familiar 3 spatial dimensions and 1 temporal dimension, new pathways for learning, problem-solving, and creative thinking would emerge. Mathematics and physics education could place greater emphasis on abstract reasoning, spatial visualization, and the development of innovative models and computational methods to represent complex, higher-dimensional phenomena. Interdisciplinary learning would flourish, bridging gaps between mathematics, physics, computer science, and philosophy, and encouraging students to interrogate the nature of consciousness, perception, and reality itself. Educational approaches might integrate virtual and augmented reality technologies, allowing learners to engage interactively with higher dimensional objects and spaces, making once abstract concepts vivid, tangible, and immersive. Should higher dimensional control be confirmed, the implications for human society would be seismic. Scientific paradigms would undergo a radical transformation as researchers seek to understand and perhaps harness these forces, spurring massive investments in physics, cosmology, and allied disciplines. Religious and spiritual beliefs would confront profound challenges, with some interpreting higher dimensional control as evidence of divine orchestration, while others struggle to reconcile their doctrines with a universe more complex than previously imagined. Entirely new belief systems could arise, focused on the existence and influence of higher dimensional entities. At a societal level, the revelation of such forces could provoke widespread existential questioning, shifting perceptions of free will, destiny, and humanity's place in the cosmos. While some might experience disorientation or anxiety, others could feel a renewed sense of unity, purpose, and cosmic connectedness, reshaping social cohesion and human priorities on a planetary scale. Human relationships might also be transformed under the lens of higher dimensional influence. If our interactions are subtly guided by forces beyond conventional perception, the nature of choice, compatibility, and serendipity would require re-examination. Romantic, familial, and social connections could be viewed as orchestrated events within a higher dimensional framework, potentially explaining phenomena such as déjà vu, instantaneous bonds, or inexplicable affinities. This perspective could foster a more holistic understanding of interpersonal dynamics, framing each encounter as part of an intricate, multidimensional tapestry where individual choices are interwoven with cosmic patterns. Yet, the scientific community would approach these ideas with careful skepticism, recognizing that while higher dimensions are a well-established concept in theoretical physics, any direct influence on human behavior remains speculative and unproven. The potential reality of higher dimensional control thus opens a vast, uncharted landscape of intellectual, social, and psychological exploration. It challenges conventional notions of autonomy, governance, and knowledge while offering the possibility of a more profound connection to the cosmos. Whether it engenders awe, fear, curiosity, or existential reflection, the acknowledgement of forces beyond our perceptual reach could reshape every facet of human life, inviting us to reconsider the nature of reality itself and our role within an infinitely complex universe. As we continue to explore the vast and intricate nature of our universe, we find ourselves on the threshold of revelations that could fundamentally bridge the divide between abstract, theoretical higher dimensions and the tangible realities that govern human relationships. The notion that influences from higher dimensions could permeate our three-dimensional existence carries profound implications not only for physics, but for the economic structures that underpin society. If unseen entities or forces originating from dimensions beyond our perceptual grasp were able to interact with our world, they could revolutionize our understanding of scarcity, abundance, and value itself. Economic models, long based on finite resources and predictable market behavior, might become obsolete if higher dimensional interventions unlocked sources of energy or materials that were previously unimaginable. Such a shift could transform the way humanity measures wealth, allocates resources, and even defines necessity, potentially dismantling entire industries while simultaneously creating entirely new sectors of commerce. Financial markets might experience volatility on scales never before observed, driven by variables that exist outside the realm of our current predictive frameworks. Supply and demand could no longer be considered purely human constructs, as higher dimensional entities, operating under principles beyond our comprehension, might manipulate the flow of goods, services, and energy in ways that seem paradoxical or miraculous. Beyond economics, the potential for higher dimensional communication or travel could fundamentally alter trade, labor, and governance on a cosmic scale. Human civilizations might find themselves compelled to adapt, compete, or cooperate with entities whose physical and economic principles are utterly alien, reshaping interstellar alliances, redefining comparative advantage, and redefining the very essence of global or even universal power dynamics. Several competing frameworks attempt to explain phenomena attributed to higher dimensions, each offering unique insights. String theory, for instance, proposes that the universe comprises 10 or 11 dimensions, most of which are compacted and curled so tightly that they elude direct perception. According to this theory, fundamental particles are not point-like dots, but tiny, vibrating strings, whose vibrations manifest as the forces and particles observed in our reality. In contrast, loop quantum gravity rejects extra dimensions, instead depicting space-time as a complex network of loops and lines at the quantum scale, striving to reconcile general relativity with quantum mechanics without the need for hidden dimensions. The holographic principle introduces yet another perspective, suggesting that our three-dimensional universe could be a projection of information encoded on a two-dimensional surface, akin to how a hologram generates a three-dimensional image from a flat plane. This concept challenges our intuitive understanding of dimensionality, hinting that higher dimensions may not be separate realms, but emergent phenomena derived from more fundamental, lower-dimensional systems. The exploration of parallel universes or multiverses further complicates the picture. While these ideas are not always directly tied to higher dimensions, they often intersect with them, offering alternative explanations for observations in cosmology and quantum mechanics. The holographic principle and higher dimensional models each illuminate different facets of reality, one suggesting that all information within a volume of space is encoded on its boundary, the other proposing that our universe exists within a larger, possibly infinite framework of dimensions beyond the familiar 3 spatial and 1 temporal dimensions. These extra dimensions may be microscopic and curled up, or vast and expansive, invisible, yet profoundly influential. Some theorists even attempt to reconcile these frameworks, proposing that our perceived reality might be a holographic projection derived from higher dimensional structures, a synthesis that pushes the boundaries of physics and our understanding of the cosmos. The anthropic principle further adds to this tapestry of speculation. It posits that the observable universe must possess the properties necessary for conscious life to exist, as only in such a universe could observers contemplate its nature. This principle highlights the apparent fine-tuning of cosmic constants and physical laws, provoking debate about whether this precision arises from chance, necessity, or some form of overarching design. Minor variations in fundamental forces or particle properties could render life impossible, prompting discussions about multiverses, cosmic selection, or even purposeful orchestration. Critics dismiss the principle as a form of observational bias, yet its proponents argue that it provides a lens through which to understand why the universe appears so precisely calibrated for life. The anthropic principle bridges the scientific and philosophical, inviting reflection on our place in the cosmos and the extraordinary conditions that make our existence possible. Simulation theories extend these ideas into provocative territory, proposing that reality itself could be an advanced computational construct maintained by higher dimensional architects. If such entities exist, their capabilities could render phenomena we perceive as miraculous or incomprehensible entirely ordinary within their frame of reference. From our vantage point, these manipulations might manifest as the fundamental laws of physics, quantum oddities, or other enigmatic phenomena, suggesting that our understanding of reality is but a small window into a far larger, more complex system. This intertwining of higher dimensional influence and simulated realities raises profound questions about consciousness, existence, and the very nature of perception, challenging humanity to reconsider the boundaries of what is real. The apparent fine-tuning of the universe has spurred diverse hypotheses, including the multiverse theory, where countless universes exist with varying physical constants, and the notion that fundamental constants may evolve across time or space. These perspectives, alongside ongoing research in string theory and quantum mechanics, may ultimately reveal deeper, underlying principles that account for the universe's delicate balance, without invoking cosmic coincidence or purposeful design. The quest to resolve these mysteries continues to drive cosmology, pushing scientific inquiry to ever more ambitious horizons. Cyclic universe models offer yet another lens, suggesting that our cosmos experiences endless cycles of expansion and contraction, repeatedly undergoing big bangs and big crunches. In this view, the universe requires neither higher dimensional control nor external intervention, as each cycle resets the cosmic clock, offering a rhythm to existence that is both infinite and self-renewing. These models, alongside higher dimensional theories, holographic principles, simulation hypotheses, and multiverse conjectures, collectively illuminate the extraordinary complexity of the universe, challenging every assumption about space, time, and the very essence of reality itself. This repetitive cycle unfolds entirely within the familiar four dimensions of space and time, suggesting that the universe may operate without requiring additional dimensions to account for its origin or ongoing evolution. In these self-contained cyclic models, the fundamental laws of physics alone could suffice to govern the universe's behavior across endless sequences of birth, expansion, collapse, and renewal. Such a framework diminishes the need to invoke external forces or higher dimensional mechanisms to explain cosmic phenomena, offering a vision of a universe that sustains itself from within. Yet these cyclic scenarios face formidable questions, particularly about how information, energy, and physical laws persist intact from one cycle to the next. Despite these challenges, cosmologists remain captivated, exploring the idea that the universe could perpetually reinvent itself, a grand rhythm echoing across the eons. Quantum entanglement, meanwhile, presents one of the most enigmatic and tantalizing features of the cosmos. This quantum phenomenon binds particles together in ways that defy classical intuition. When two particles are entangled, the state of one instantaneously reflects the state of its partner, no matter the vast distance separating them. Observing one particle instantaneously conveys information about the other, even if they lie on opposite ends of the universe. Some theorists suggest that entanglement might underpin a hidden interconnectedness spanning the cosmos, weaving every particle into a vast, invisible web of information. If this holds true, the universe itself could be viewed as a single, interlinked quantum system, where events in one region subtly influence distant corners through this unseen network. Skeptics caution that the delicate nature of quantum states might prevent entanglement from persisting over cosmic scales, or surviving the chaos of macroscopic systems. Nevertheless, this concept continues to propel research into the fundamental structure of reality, pushing scientists to explore how space, time, and information might be intertwined in ways we are only beginning to grasp. Emergent gravity theories propose a radically different perspective. Gravity may not be a fundamental force at all, but an emergent property arising from the collective interactions of underlying quantum processes. In this view, space-time and gravity emerge much like fluid behavior arises from the coordinated motion of innumerable water molecules. Considering higher dimensional influences in the context of emergent gravity opens even more profound possibilities. Some models suggest our observable universe may float within a higher dimensional space, where the behavior of gravity is a projection of interactions occurring in these extra dimensions. Imagine our four-dimensional cosmos as a membrane drifting through a multidimensional bulk. The gravitational effects we perceive could be shaped by unseen dynamics operating in this higher dimensional realm. This idea resonates with certain string theory frameworks, where extra dimensions are mathematically necessary to unify physical forces. The interplay between emergent gravity and higher dimensional influence hints that what we call gravity might be a shadow of deeper, more intricate processes, hinting at a universe far richer and more complex than the one we perceive directly. The notion of higher dimensional control has intrigued scientists and philosophers alike for decades. Proponents argue that phenomena or entities residing in extra dimensions could subtly govern or influence the behavior of our observable reality, potentially illuminating mysteries like the nature of dark matter or the apparent tension between quantum mechanics and general relativity. Mathematical elegance further supports these ideas. Theories such as string theory require multiple dimensions to reconcile fundamental forces into a cohesive framework. Yet skepticism remains. The principal objection is empirical. Despite extensive experimental effort, there is no direct evidence of extra dimensions exerting observable effects. Critics note that invoking higher dimensional control may violate the principle of simplicity, introducing unnecessary complexity when conventional explanations might suffice. The tension between these perspectives fuels ongoing inquiry, inspiring both theoretical innovation and experimental ingenuity. The coming decade promises transformative insights into higher dimensional physics. Theoretical physicists continue to refine multi-dimensional models, pushing beyond the familiar three spatial dimensions and one temporal dimension. String theory posits the existence of 10 or 11 dimensions, each potentially harboring profound implications for the underlying architecture of reality. With advancing computational power and new mathematical techniques, researchers may begin testing predictions of these theories, opening the door to empirical verification of concepts long confined to abstract mathematics. Quantum computing adds another dimension to this exploration. These machines operate on principles that challenge conventional notions of space and time, and increasingly powerful quantum computers may allow simulations of higher dimensional systems previously beyond reach. Observational cosmology may also yield crucial evidence. Subtle imprints in the cosmic microwave background or unexpected behaviors of gravity on grand scales could betray the presence of hidden dimensions, reshaping our cosmic perspective. Research into higher dimensions could catalyze fundamental shifts in physics. One transformative possibility is the unification of forces, reconciling gravity with quantum mechanics into a seamless framework. Another is the reimagining of dark matter and dark energy. What appears invisible and inexplicable within our familiar four dimensions might, in higher dimensional terms, be ordinary manifestations of extra-spatial dimensions influencing the universe in subtle, pervasive ways. The exploration of these hidden realms promises not just new knowledge, but a profound transformation in our understanding of existence itself, revealing a cosmos far more intricate, interconnected, and astonishing than previously imagined. The nature of time itself could undergo a profound transformation through research into higher dimensions. We may come to understand that time is not a singular, linear entity, but rather a rich, multi-layered tapestry with intricate branches extending in ways we have scarcely imagined. Such a revelation could upend long-standing theories about the universe's birth and evolution, challenging our current understanding of the Big Bang, cosmic inflation, and the very architecture of space-time. Beyond that, higher dimensional studies could radically shift our perception of parallel universes and the multiverse. Instead of seeing other realities as isolated, disconnected pockets, we might discover that they coexist within higher dimensions, accessible under specific physical conditions, opening entirely new fields of research and technologies that could reshape humanity's role in the cosmos. Exploring the idea of a higher dimensional control carries profound implications for our understanding of existence itself. If such control were proven, it could fundamentally alter our perception of reality and our position within it. It suggests that our familiar three-dimensional world may be influenced or even guided by forces or entities operating in dimensions beyond our perception. The confirmation of higher dimensional control would compel a reevaluation of physics, philosophy, and spirituality, potentially providing explanations for phenomena that currently defy scientific explanation, including quantum entanglement and the enigmatic nature of consciousness. This discovery might challenge our very notions of autonomy, implying that what we consider free will could be subtly shaped by higher dimensional factors. Conversely, if higher dimensional control were definitively disproven, it would reinforce the view of the universe as a self-contained system governed entirely by known physical laws. This outcome would redirect our efforts toward alternative explanations for unresolved phenomena, stimulating innovative research within the framework of observable dimensions. Regardless of the result, the act of investigating higher dimensional control stretches the limits of scientific and philosophical inquiry. It encourages us to question assumptions, devise new investigative tools, and deepen our understanding of existence. The pursuit itself expands our worldview, fostering intellectual growth even if ultimate answers remain elusive. As scientists probe higher dimensional mysteries, the ethical implications of this research become paramount. Discovering that our universe is merely one of countless others in a vast multiverse could dramatically alter our sense of purpose and place within existence, raising the risk of philosophical upheaval or existential anxiety. Equally pressing is the need for responsible application of technologies derived from higher dimensional studies. Any methods that allow manipulation or interaction with these dimensions could have profound, unpredictable consequences, necessitating rigorous protocols and safeguards. Resource allocation also demands careful consideration. While the pursuit of higher dimensional knowledge is undeniably captivating, it must be balanced against other urgent scientific priorities and societal needs. Meticulous risk assessment and precautionary measures will be essential to navigate the uncertainties inherent in this frontier. Maintaining a balance between speculation and scientific rigor is critical when exploring cosmic concepts. Researchers must navigate the fine line between expanding the boundaries of knowledge and adhering to the disciplined methods that underpin credible science. Hypotheses must be grounded in observation and existing knowledge, with experiments or predictions that can be tested or falsified. Yet, the study of higher dimensions often ventures into realms beyond direct observation, relying on mathematical modeling, computer simulations, and extrapolations from established physics. These speculative explorations are invaluable, guiding future research and inspiring fresh approaches to understanding cosmic phenomena. Transparency regarding the certainty of different ideas allows scientific progress while preserving integrity, ensuring that curiosity and creativity do not eclipse verifiable evidence. Public engagement plays a crucial role in this dialogue. Concepts of higher dimensions have far-reaching implications for our understanding of reality, and translating these complex ideas into accessible language fosters curiosity, critical thinking, and scientific literacy. Involving the public bridges the gap between cutting-edge theoretical physics and everyday comprehension, demystifying abstract principles while highlighting their potential impact on our worldview. Exposure to these transformative ideas can inspire new generations of scientists and thinkers, sparking innovative solutions and novel perspectives. This exchange of ideas between experts and the wider community fuels progress and deepens societal appreciation for the complexity of the universe. The exploration of higher dimensions is propelling science into uncharted territories, promising a radical reshaping of our understanding of the cosmos. This quest is far more than an abstract mathematical exercise. It is a fundamental search that may unlock the deepest secrets of reality. Theoretical physicists are leading the charge, employing advanced mathematics to model universes with as many as 10 or 11 dimensions, most imperceptible to human senses. Comprehending these dimensions could resolve long-standing mysteries, such as the relative weakness of gravity, the reconciliation of quantum mechanics with general relativity, and the elusive nature of dark matter and dark energy. Such insights carry the potential for breakthroughs in particle physics, cosmology, and the origins of the universe itself. Moreover, higher dimensional research is already inspiring technological revolutions. Quantum computing, leveraging principles of quantum mechanics, exploits higher dimensional spaces for processing information in ways traditional computers cannot. Advancements in this field have the potential to transform cryptography, accelerate drug discovery, enhance modeling of complex systems, and revolutionize both industry and scientific methodology. In this light, the pursuit of higher dimensions is not a distant theoretical exercise, but a tangible frontier, shaping the future of human knowledge, technology, and our understanding of the cosmos itself.